So, good morning to all of you. This will be an English day, as it would be pretty troublesome with a lot of interpreters. I hope that will be okay for most of you. Welcome you to this ECOnnect final seminar day, where we have a schedule of. My name is Bent Christensen. I am the moderator of today. So if there is anything you want to say or add, come to me first, please. We're not on a super tight schedule, but we're on a. I should never have said that. We're on a tightish schedule. So please come back from the breaks and the lunch in time. And to the speakers, please keep at least somewhat in your time spot. The morning session starts now. We have presentations up to lunch. We have a break at 10 past 10. Lunch is an hour from 11:30 to 12:30. Lunch is down there in the entrance floor, and coffee, which you can have during breaks, or just outside the door. We have an afternoon session with presentations for the first part of it, an hour or so, and then we have a break. Probably pretty wrong there in the time. It's till 20 past 2, not till 2:30. Because there will be a panel discussion from the last 40 minutes of today, and then we will end it off with some final words at 3 o'clock-ish. We have the ECOnnect contacts here. Today is Emma over there. Please do something. We have Johnny Berglund, which also should rise and shine. And we have Jani Särkkä. So if there's any practical stuff that you want to bother anyone with, these are the go-to guys. Please use them wisely. What are the practicalities of today? Well, there are some. There's a digital platform that Emma will talk more about. There's also a real, what do you call it, IRL background. In the other room, there's an exhibition which contains much of the stuff that's online. So you are most welcome during the breaks to go and watch them. There's a picture taken by Anina, among others. So almost a seahorse. Well, lunch was down there, coffee out there. Toilets are very clearly marked, so I expect absolutely no mistakes today. There are 2 doors that are marked with toilets. Smoking, you never have to talk about that anymore. That's nice. I would really appreciate if you all would check your phones, that they are on silent. And if they are not, please shut them up the moment they start to make sounds. There is no code for Wi-Fi access if you need Wi-Fi. Wi-Fi is, what was it, something easy? Scandic Easy. Well, that makes sense, as we are in Scandic Hotel. Scandic Easy, no code if you need it. I think that was about. Something you want to add, Emma? Or have I remembered most of it? I think so. I think so. So what's this about today? Well, I'd like to show you just some pictures of the place we're talking about, the more or less Kvarken, Botnia-Atlantica, which is a very young part of the world. Species poor, brackish water, with very short time for adaptation of the living organisms, creatures here. It's beautiful at times, loads of small islands, loads of not really yet small islands, which those that have boats know very much about. There's a large amount of the year where there's ice on here, and we have species that are dependent on it, such as the ring seal needs the sea ice in order to be able to breed. The dog is not. It's just. Well, it's in most of my pictures, though. So it happened to be there. We have clear effects of land rise, which you can see there. We have quite a number of very interesting birds, even in a greater perspective. With the parasitic skuas, we have the I have no idea what the barnacle geese. They are called barnacle geese, which has been more or less gone for many years, but are now doing in a very, very quick rise out here in the archipelago. We have where did that come from? We have the northernmost, what do you call it? Bird mountain? Fågelberg. It's not called the bird mountain. Fågelberg, with a lot of those fish-eating birds down in further down south, which is an amazing thing to watch. A lot of fisheries out here, both professional and what do you call it? Fritids. Well, hobby fishing, with seek as one of the, smoked seek as one of the main catches. We also had a recovery of a number of very, very threatened animals during the last decades, such as sea eagle here. 1970-something, we had zero sea eagles breeding in Västerbotten, absolutely zero. Now we have a crap load. They are at the level of Kvarken. It's full. There are no more apartments. They really have to expand inland to be more of them. There are in the islands I showed you. There are 8 breeding pairs, which is as close population as anywhere in the world. Basically, you cannot go out on Kvarken without seeing them. We have this land rice. This is from Höga Kusten, which wasn't Höga Kusten for a long time. Now it is. It's about 200 meter Höga Kusten or 180 meter Höga Kusten, which is an interesting feature when you are a sailor or have a boat. That all these rocks underwater suddenly is not underwater. Well, the problem is not when they're not underwater. The problem is mostly when they still are just underwater. Which you see, and many people use this as a recreational basis for summers, winters, and whatever they do. Loads of boats out here with people that think this is important. It's also used for swimming. So that's some kind of a perspective of what we are, where we are situated. Very important to very many people, and. Emma Andersen from Metsähallitus. I nailed that one. I really nailed that one. Will now tell you more about the project per se. The stage is yours, Emma.
Thank you. So we will first show a video that we have produced in this project, a short introduction to the Baltic Sea.
I am the Baltic Sea. I consist of salt water and fresh water. My water is a unique habitat which you cannot find anywhere else in the world. I do not have colorful coral reefs, but I have forests of my own. These underwater forests are my lungs. Together with others who live here, they clean my water and make it clear. I can storm like any other ocean, but I'm also vulnerable. I am vulnerable to threats such as pollution and eutrophication, which cloud my waters. I give you people so much, but I'm also a home for others. Mussels, fish, algae, birds, mammals, and others live in my kingdom. Like you, I want to keep my home safe and clean. My threats are only growing bigger because of the changing climate, the change you are causing. I'm getting warmer, my ice cover is getting thinner, and my nature is changing. I will adapt and survive the changes. I will remain the Baltic Sea. but the changes can be too much for those living within me. And for you.
Yes, hello everyone. My name is Emma Andersen, and I have for the last 1.5 years been working as ECOnnect's project coordinator, and I will now give you a short introduction to the project. The project has been an Interreg Botnia-Atlantica project which started in 2018 and will end now in May 2022. And we have been 4 partners working on this project: the South Ostrobotnian Center for Economic Development, Transport and Environment, Västerbotten and Västernorrland county administrative boards, and Metsähallitus, who has been the lead partner. We are now around 12 people working on the project, but there's been several others contributing to the work over the time. The aim with the project has been to study how climate change might affect the central Gulf of Bothnia by the end of the century. Changes in, for example, water temperature, ice cover, and maybe salinity as an effect of climate change could lead to a range shift for several species. And for this reason, it is important that we ensure the functionality and resilience of marine protected areas. The climate models used in this project was produced by SMHI and FMI, and they focus on the worst case climate scenario, the RCP 8.5, and HELCOM's nutrient reduction scheme, the Baltic Sea Action Plan. So this is the future we could expect to see if we manage to tackle the local eutrophication problem in the Baltic Sea, but we don't succeed in reducing global greenhouse gas emissions. The target group for the material produced in this project has been people working, for example, with climate adaptation and community planners and other experts who could use this data in their work, but also the general public. And here you can see a map of the project area, which is in the central Gulf of Bothnia. And between Umeå and Vasa, you find Kvarken, which is a shallow transitional area separating the Bothnian Sea from the Bothnian Bay. The area is shaped by the ongoing land uplift, which makes the land rise at around 9 millimeters per year. And the archipelago on the Finnish side is shallow with thousands of small islands, whereas the coastline on the Swedish side is steeper with fewer islands. And there are several marine protected areas within the project area. So why are we focusing on this area? The area is special as there is a low mean salinity, around 3 to 4 per mil in Kvarken, and this low salinity is not optimal for either marine nor freshwater species. And we already have several marine species that are living on the border of tolerance for low salinity. So you can see here on the map that, for example, blue mussel and bladderwrack and narrowback do not occur more north than Kvarken. So in the future, if we will have a change in salinity, we could also have a change in species distribution. Seasonal variations in water temperature and ice cover also has a great effect on the environment and the species. The mean depth in the project area is 64 meters, and the shallowest part is Kvarken, which is an important route for species to spread between Finland and Sweden. We have had 3 different working packages in the project. We have modeled the future of the underwater environment. We have looked at ecosystem services and predicted how these might change in the future. And we have also analyzed ecological connectivity and the resilience of the network of marine protected areas. And you will hear presentations about each of these packages later today. So I would like, from my side and the project group side, wish you all a very warm welcome to this final seminar. And we have some people here with us in Umeå, but we also have several people with us online. And we have created, together with Umeå Congress, an online platform where you can take part in the seminar. And we also have a coffee room where you can go and discuss different topics during the fika breaks, and then we have a separate group for the exhibition where we have uploaded all the material, and you can also find the links to our story maps. Thank you.
Thanks, Emma. Thank you very much. Any questions for Emma? Now you have her here on stage. Otherwise, we will. This is a slightly complicated day, as we have, as Emma was talking about, have a number of audiences online, but we also have some of the speakers online. So we'll just have to. Well, you know, we're not in. What are we? We're in pre-post COVID. So you. You're probably are pretty used at this. There are some amazing screw-ups on making stuff work, but we have some technicians that are very much doing whatever they can to make this work. The next speaker will be Sam Fredriksson from SMHI. He will be online. He is an oceanographer, and he is, as far as I know, I don't know Sam, but he seems to be working with a lot of stuff. But I think in the context of this project, he works with models studying greenhouse gas transfer between water and air, which obviously is quite an important part of this whole story. So, do we have Sam online? Is that a?
Yeah, I hope so.
Oh, hi. Hi, Sam.
Can you hear me?
Welcome. We can hear you very well. Can you hear us?
Yes.
Oh,
thank
good.
you.
So, Sam, I don't know if you see me. I'm the one in the bluish thing here. There.
Yes. Yeah.
So, when you have about 2 minutes left, I will. You too. Well, we
Seems
prepared
like we
this.
have the same choice then.
We prepared this. I will do something like 2 minutes, 1 minute, and then. So there is a countdown in severity here. Welcome, Sam. The stage is yours now. You have, I would say, about 20-ish minutes to speak. Is that your perception of it?
Yeah, I thought I had something like 30, but I will speak a little bit faster.
It's a common comment today, Sam. So welcome.
Thank you. Yeah, so good morning, and thank you so much for inviting me and Lars Arneborg from SMHI to your final seminar, ECOnnect. I will present some of our results, and Lars will participate in the panel later on. So here's there in person, whereas I this time will do the presentation online, as you can see. I will try to answer any questions in connection to the presentation, but there are, of course, good opportunities to talk to Lars in Umeå as well. And my idea is that we take the questions after the presentation, since I'm online, and therefore, according to at least my original plan, left a few minutes to this in the end of the presentation. The work we're about to present started up in the SmartShape project, which is where we, FMI and SMHI, produced climate predictions, and it's a project that aimed to deliver science-based guidance for sustainable use of the Gulf of Bothnia. And then in 2020, we had the opportunity, due to funding from ECOnnect, to continue extend our climate scenarios from reaching 2060 until the end of the century, which we are very grateful for. We could, however, not extend it to the whole ECOnnect period 2021-20 due to lack of model forcing for the last 20 years. So, for you who want to have main findings directly, we did the first slide of the main findings right away. So, first of all, temperature. It will increase as the climate changes. Sea surface temperature will, however, continue to be cooler during winters, as long as the temperature continues to be cold during winters. Salinity seems to decrease, here is, however, still large uncertainties and a large spread within the ensemble members, including change of sign, meaning that some models even project a salinity increase. It should here also be noted that sea level changes have not been considered here in the model. Both when it comes to ice, both observation and projections indicate the trend of thinner and smaller area of ice coverage. Despite this, there will, however, even during mild winters, be ice in the north of Gulf of Bothnia. And to the right, I guess you can't see it, but it's a summary of fact sheets that has been produced within the Smart Sea project. And here you can also see two links, the one in Swedish and one in Finnish. So please go in there and have a look with a little bit more thorough analysis and background, and also for different things than the variables I talked about right now. And just before we go to the outline, I just wanted to show you the goals of Smart Sea. They were to locate key areas of natural resources and ecosystems, assess, estimate physical, biochemical, and human activity changes, assess impacts, risks, and opportunities of climate change, provide solutions to enhance energy and food production, interact with marine spatial planners, industry, local authorities, and policymakers. And by that, provide roadmap for sustainable use of the Gulf of Bothnia. And as you can see down there, there's a lot of participating organizations. So the outline for today is I will start with the introduction of climate scenarios, how they are produced, and some forcing. And then we'll discuss the circulation of Gulf of Bothnia. Hopefully you can see the animation here to the right. I will discuss that a little bit more thorough later on. And then we'll discuss trends, future trends in river inflow, temperature, salinity, ice, and oxygen. And then end up with some summary and questions if we have time for that. Yes, and some of the plots here, they are to be published quite soon. So yeah, please ask if you want to use them. So we have been using in the Smart Sea and ECOnnect projects, local effects are studied. And in order to do so, it's necessary to use a rather high resolved model climate model. And to the left here, you can see the model domain, and we have been using this Nemo-Scobie. Let's see. And this resolution of the model is about 1 nautical mile in horizontal, which means about 2 kilometers, and it has 56 vertical layers. But it needs forcing, and it needs forcing both from the atmosphere, temperature, wind, rain, and nutrients, and land, river flows and nutrient loads, and boundary conditions at the southern boundary, open to the Baltic proper. And then it delivers properties as temperature, salinity, ice, nutrients, also phytoplankton, zooplankton, second depth, primary production, oxygen concentrations. But this model needs, however, input forcing from other large-scale global models to work. And the work process is therefore to use results from large-scale global models and downscale these via atmosphere-ocean coupled regional models. You can see here in the center. That in turn can be used in local model, and then in turn can be used to perform different kinds of ecosystem analysis that has been done here in the ECOnnect project. So within the framework of IPCC, the Intergovernmental Panel of Climate Change, There have been conducted a number of studies using different GCMs, global climate models, for different RCPs, representative concentration pathways. I guess a number of you have heard of this before. In this way, the climate community can get a better statistical representation of both uncertainties in different models and different greenhouse gas emission scenarios. In the Baltic project that forms the basis of the forcing for these climate predictions, 4 GCMs and 2 RCPs were used. After these, we have run all 4 GCMs in this project as well. But in the analysis, mainly used only 3, since the IPSL model C here does not contain any RCP 8.5 results. And the periods we have been using is for the hindcast, 1980 to 2005, and the history is 2076 to 2005. And then in the project, in the results you will see later on, it's either the later period, 2070 to 2100, or sort of the Smart G period where we started up 2013 and 2016. But it's not only for the, what we've seen so far is for the physics, but we have also for the nutrients, need to have forcing. And as it is, the nutrients comes from land, and the runoff is affected by the RCPs. But it also that the nutrients are affected from the actual concentrations, not only the runoff. So therefore, we have different nutrient scenarios as well that affects the nutrient concentrations in the river that then in the end affects the nutrient loads. So in this project, we have used the Baltic Sea Action Plan, called as sort of a sustainability scenario. And we have used in the Baltic app called Worst Scenario, which is a fossil fuel development, which we here called the high scenario. But as said, we also need boundary data, and that data is taken from the Baltic Up project, where we performed a climate scenario with the RCO-SCOBY model, which is with a slightly less resolved model, 2 nautical miles in horizontal. And this boundary data includes both physical and biochemical data. And here you can see the RCO-SCOBY domain is both light blue and dark blue, whereas the Smart Sea domain is the dark blue. So here is the boundary where the data from the RCO-SCOBY model is used for the Smart Sea model. So circulation of Gulf of Bothnia, I have here chosen to use the hindcast just to sort of set the scene for the circulation. And it's divided into 2 basins, where both have a cyclonic, a counterclockwise surface current, as you can see here to the left. And in these 2 plots, we can to the left see the latitude in the x-axis and the depth at the y-axis. And here we have the meridional flow, that is the integrated flow in the west-easterly direction. And we can typically see here that we have, oh, sorry. I can see, sorry for that. I can see I shifted the directions of the arrow. So it's actually the red one should be directed northward and the blue one should be directed southward. So we have a bottom current with dense water going northward, and then we have a surface current going southward. Sorry for that, for the sign of the arrows. So that is what can be seen on the left-hand side plot. On the right-hand side, we see a depth integrated flow. So that's sort of if you've seen from the above, all the flow from the surface to the bottom going in either direction. And here we can see that it's typically we have an inflow at the eastern side of the Botnian Sea and an outflow of the western side of Botnian Sea. So we here, by adding these two plots, you can see that there is sort of a three-dimensional, a little bit skew overturning circulation. And then we have also the sort of wanted to show how this looks in salinity space. So here in the x-axis, once again, I have actually wrong sign of the arrows, sorry for that. But in the x-axis, we have latitude, and in the y-axis is salinity. So once again, it's shown that we have an inflow of saline and dense water along the bottom, both in Botnian Sea and Botnian Bay, however, in different salinity levels, and outflow at the surface with more fresh water. Once again, both in Botnian Sea and Botnian Bay. Sorry for the arrows. So to sum this up, we have regarding circulation, there is a surface horizontal circulation in both Botnian Sea and Botnian Bay, which we think is interesting for dispersal and connectivity studies. This is stronger during winter than summer, but it's visible also during long time averaging. There is also a monodal overturning circulation that transports saline bottom water northward and fresher water southward. And when it comes to flow speed and the trend, we can see that the mean flow speed and its standard variability are increasing towards the surface. Monthly averages used in those analyses. And both are increasing for RCP 4.5 and even more for RCP 8.5 with a magnitude of something like 10%. And max speed increases more than mean speed here. So for the trends of river inflow, we can see it's larger river inflows in both RCP 4.5 and RCP 8.5, but it's more pronounced for RCP 8.5. When it comes to sea surface temperature, to the left, we see the historic mean, and then we have the differential plots for RCP 4.5 in the middle and 8.5 to the right. And we can see that there's a clear increase in both RCP 4.5 and 8.5. We can see a small tendency of small increase in coastal areas, which we think is due to that the ice, which we'll see later on, the ice change is smaller along the coastlines than in the central part of the basins. And here we can see the same plots, but for sea bottom temperature. And once again, we can see there's a clear increase in both 4.5 and 8.5. Here we can see that it's a tendency to larger increase in the shallower areas. When it comes to sea surface salinity, to the left, we can see the salinity for the historical run. And to the right, we can see the differential plots. And we can here see that's a decrease in both 4.5 and 8.5, with a tendency to a smaller decrease in Kvarken and in the Botnian Bay. And here is for bottom salinity. Once again, there is a decrease for both 4.5 and 8.5. There is a tendency to smaller decrease in shallow areas in Botnian Bay. Summary, temperature, increase in both sea surface temperature and sea bottom temperature. Sea surface temperature increases less in coastal areas, especially along the Finnish coast. sea bottom temperature increases more in shallower areas. And when it comes to salinity, decrease in both sea surface salinity and sea bottom salinity. It's, however, a less decrease in quark and shallower areas. But it's, as said in the beginning, there's a large spread within the ensemble, including change of sign. So this, it should be taken into account when using these salinity changes in the analysis. So here it's for the ice, and we have chosen to show the length of ice season. And at the x-axis, we have the time, and in the y-axis, the number of days with ice cover. And here we have stations from north to south, so here's Kemi, the most north one, Kalajoki, Sälgrund, Kymäpiljaja. Sorry for that. And what we can see here is both observations, the reference run, the historical, and the projection run show a decrease in trend in both length of ice season and actually ice thickness, however not shown in these plots. And here is also a map of the sea ice extent. Here's not differential plots, but here's because that's quite difficult to understand when it comes to sea ice extent. So here we have at the left-hand side the actual sea ice extent for during the historical period, and here is for during RCP 4.5 and 8.5. And but please note here as well that this is not for the end period, but for the 2030 to 2060. We see a clear decrease in both 4.5 and 8.5. And said before, we can see the tendency of remaining ice in coastal areas, the larger changes in central part of the basins. So ice short overview, length of ice season, observations, historic and projection runs show a decrease in trend in both length of ice season and ice thickness. And for sea ice extent, there is a decrease in both for both 4.5 and 8.5, and tendency of remaining ice in coastal areas rather in the central parts. Very short, briefly, oxygen concentration. So we can see here that's two stations. The one marked with red rings to the left-hand side there. And once again, we have years in the x-axis and oxygen concentrations at the y-axis. And the dots are his observations in this, the black one historical. And then we have the different RCPs, but here also with different nutrient scenarios. So RCP, or we can say for the BSAP, nutrient scenario, that's sort of greenish, whereas the high nutrient scenarios is red and yellow. So we can see here on those plots that the historical period and observations match very well. Perhaps the variability in the model a little bit less than observations for the station F9. We can see that we have higher oxygen concentration in F9, Botnian Bay, than SR5, the Botnian Sea. We can also see, I can at least see, I hope you can see it as well in the plots, but there is we can see here and also in other plots that the nutrient scenario affects more than a climate scenario. And it's, I would say it's especially visible in this one, but it's typically a little bit more greenish in the upper parts, whereas it's more yellow-red here in the lower parts. Yes, so it's a general large variability, and we get a little bit closer to oxygen deficient bottoms in Botnian Sea for high nutrient scenarios in the end of the period. So summary and in short, what's said already in the beginning. So the temperature, it's increasing as climate changes. Salinity seems to decrease, but still large model uncertainty. And not really just model uncertainty, it's also related to sea level change uncertainties as such. Quite consistent ice trend with decreasing both ice cover areas and ice thickness. And thank you for your interest. And here's at least a number of members of the SmartSea team, both from SMHI and FMI. And I've also underlined the persons that have been contributed with plots to this presentation. And once again, a large thank for the ECOnnect and the ECOnnect team for making it possible for us to extend the climate scenario runs.
Thank you very much, Sam. You're excellent on your time management. Thank you very, very much for making my life so much easier.
You're welcome.
We have time for one or two questions, depending on the level of time of the answers. And you there, those that are online, you're most welcome to write your potential questions in the chat. I will be very, very eager for any questions there. In here, any questions to Sam? Nothing online, no. I saw that. Okay, Åsa?
Yeah, I don't know if Sam is hearing me, but no, he can't.
So, okay, tell me and I will read. Okay, so.
Yes, so if you didn't include the sea level rise in this. You didn't include the sea level rise in the model, did you?
No, that's true.
Could you elaborate what, if you would have included that, what do you think would happen to salinity?
It's it's always sort of dangerous to do assumptions before you have done the actual analysis. But the idea is that if you have higher sea level changes, most likely you will get more major Baltic inflows with saline water. So that would, in that sense, then direct in the direction of making it more saline rather than now a decrease in salinity.
Let me just interrupt there and say that 10:30, this will be maybe not the salinity part of it, but the sea rise thing will be which I look very much forward to. Is it rising together, or is there a difference?
Okay, thank you, Sam.
Any more questions? Okay, Sam. Thanks a lot for your input. You're of course most welcome to listen to the other presenters.
Yes, I will, and have a good day.
We have we have a question here. You were almost off the hook, Sam. Sorry. Salinity changes depend on. I cannot read that. That's from Jon H. Reisman. Jon H. Reisman. Jesus, that's hard. I'm getting old. Salinity changes depend much on the boundary conditions. How confident are you with them? I guess the boundary conditions. How confident are you with the? I don't know. It could be the salinity changes, but I guess it's the boundary conditions.
Yes, you are perfectly true about that. If you mean there's a number of boundary conditions. One boundary condition, I don't know if that's what you're referring to, is the river runoff, and the other one is at the southern, of course, the precipitation, evaporation at the area as such. and then also the southern open boundary. And the southern boundary, that's data from RCO-SCOBY runs that have been performed before. Yes, I mean, how certain can we be? It's a published material. But as I said before, it's and I guess you're correct there that the conditions in both the Botnia Sea is very much influenced or affected by the Baltic proper. So what's happening in Baltic proper and the model and the boundary condition affects the conditions both in the model and of course also in reality in Gulf of Bothnia. So I would say this is present knowledge. We know that there is uncertainty in salinity, and we work to decrease these uncertainties in present work. I don't know if that's an answer.
It most certainly is. It most certainly is. And the comment was mostly referring to the salt transport through the southern boundary, but I guess you covered that some in your answer. As far as I understood your answer, you did. But correct me if I'm wrong. Thanks a lot, Sam. Hope to see you later. The next speaker is Tytti Turkia from Metsähallitus. But Tytti will talk about future scenarios, which is a wide subject. So welcome. The stage is yours, Tytti. And you have, yada yada.
Yeah, this.
Yeah,
I know. Yeah. Thanks, Bengt, for the really nice introduction. And good morning, everyone. And good morning to also all of our online participants in the digital seminar event. So next, we're going to look at how some interesting species that are now living in the project area might be affected by climate change in the future. And we have done this, these predictions for how species might react by modeling species distributions now in the present climate conditions and then also in the future under future climatic conditions. And therefore, it might be useful to start by very briefly first looking into the main idea in species distribution modeling, because that kind of understanding might help us to understand what kind of factors the models take into consideration, and also, on the other hand, what kind of factors the models don't take into account. And that knowledge then also helps us to interpret and evaluate the results. So, species distribution modeling. In this project, we have used a method called boosted regression trees modeling, shortly BRT, and it is similar to many other modeling techniques in the sense that it starts by combining extensive field data. For example, in this project, we have used more than 30,000 field observations, combining that to a set of environmental conditions. And the data that we have used in this project is mostly Velmu data in the Finnish side, and then for the Swedish side, we got it from the Shark and Martrans databases. So this is heavily relying on pre-existing data, and we in ECOnnect did only very little sampling. And then when we combine these kind of data on species, presences and absences, and environmental conditions, we can sort of statistically infer what is the response of the species to variation in environmental variables. So for example, if we use fucus as an example species, we can, with this kind of data, infer that fucus is more likely to be found in such places where salinity is rather high, where the depth is appropriate, it's not too shallow and not too deep, where there's good light conditions, relatively low nutrients, and so on. And then when we generalize these so-called response curves to the maps of environmental variables, we can sort of statistically search for places where the environmental conditions are similar to those places where someone actually found fucus. So even though this is like a complex modeling procedure and really like technical stuff, it is heavily based on the field data. And the key to how to look at, for example, this map here, is to think that these colorful areas, they picture areas where environmental conditions are similar to places where someone actually found fucus. So I've been now referring several times to environmental conditions. We have used a total of 11 of them, but all of them describe the conditions in the water column. So for example, nutrients and light availability, salinity, temperature, and so on. But what we have not accounted for is what's on the sea floor. So unfortunately, our models don't take into consideration the bottom substrate. So another key to how to look at these maps is to think that, okay, in these colored areas, all the conditions in the water column are probably suitable for the species, and the species could live there if then the sea floor happens to be the right kind. So for example, in the case of fucus, it of course needs hard substrate on which it can attach. So it is probably occurring in those areas if the bottom substrate is the right one. And then when we want to model species distribution in the future, we sort of repeat the process, but we use modeled future conditions. And that way we get to the final result, which is a map of potential suitably areas in the future. And then finally, when we compare the modeled reference period and future distributions, we can see the difference and this way try to predict how the species might react to climate change. And Sam and Emma both, I think, have already mentioned that in this project we have focused on certain future scenarios. So it's important to consider what kind of future we are looking at. And here the scenarios were RCP 8.5 and Baltic Sea Action Plan, meaning that we are looking sort of into a future where climate change has gone really bad. But on the other hand, we have managed to solve eutrophication. And when we're talking about the reference period, it's the hindcast part that Sam talked about. So it's the period from 1976 to 2005. And then the future period is from 2070 to 2099. And Sam already told about the abiotic changes that we are expecting. So I will just very briefly mention those in case some online participants have been on and off and didn't see Sam's presentation. So in the future, of course, the summers will be warmer. And in the project area, this means that the bottom water temperature during growing season is expected to increase by 3 degrees Celsius. Also, the winters are expected to become a lot warmer, and therefore there will be less ice. It could be said that most of the ice will be gone on an average future winter, but it's not totally missing, it's just more short-lived and much thinner. And then there's salinity, which is of course probably the most interesting variable, but unfortunately it's also the one which is the most uncertain and difficult to model for the reasons that were discussed in Sam's presentation and in the questions. But anyway, the set of models that we have used here, the models that SMHI ran for us, predict that salinity in the project area could decline by about half per mil unit. And finally, because we chose to look into a future where Baltic Sea Action Plan has been successfully implemented, it seems like there will be a lot less nutrients in the water. And less nutrients also mean less eutrophication, which means more light availability, less primary production. And in this way, it means a wider photic zone where photosynthesizing organisms can live. So when the conditions in the sea are changing, it can have different kinds of effects on species. So the same change, for example, the increase in temperature, it might be beneficial for some species, and it might be at the same time negative for other species. So when the sea is changing, there are both winners and losers. And maybe a bit surprisingly, our models predict that fucus might be among the winners when climate changes. And this is mostly because of the effect of ice. So on a normal winter, when in the old good days when there were loads of ice and thick ice, it sort of mechanically removes all vegetation from shallow rocky areas. And therefore these shallowest rocky areas are only like potential habitat for annual algae, because each winter all growth from the previous summer is scraped away. But in the future, if we have no ice or really thin ice, this sort of scraping effect is much smaller, and therefore it might mean that fucus can grow in these shallow areas. Another change that is really positive for Focus in the future is that if we apply the Baltic Sea Action Plan and eutrophication is solved, there will be more light available for growth. And this means that this higher Seki depth enables Focus to grow also in deeper areas in the future. So as a consequence of both of these changes, it seems that Focus could grow on a wider range of depths in the future, both in shallower and in deeper areas. And that is why the maps predict a big increase in potentially suitable areas for Focus. But this is a very different kind of result than many previous studies have got. So many previous modeling studies on Focus have concluded that actually climate change will be bad for Focus. And yes, there are also these negative effects. So the key difference between our study and many previous ones lies in the effect of ice and also then this much smaller decline in salinity. So we also did a test set of models without the effect of ice, and those models predicted that Focus could rather decline than increase. But we are kind of confident by using this full set of models where ice is included, because first of all, it is kind of really certain in a way that any future predictions can be certain that ice is going to be reduced. It is a relative, sure change, and also the negative effect of ice on Focus is a real thing. And the other thing, the salinity, well, the salinity prediction that we used is much smaller decline compared to some other ones. And also we have here modeled Focus on a general level. So this is including both Focus vesiculosus, the bladderwrack, and then Focus radicans, which is the closely related species that tolerates much lower salinity. And therefore it might be that actually Focus vesiculosus could be declining, but Focus radicans still tolerates the lower salinity in the future. But it's good to keep in mind that, okay, there are these uncertainties, and there are both positive and negative changes for Focus in the future. And it is difficult to say what the net effect of all of these changes might be. Then we have another species of algae, which is reacting kind of similarly to Focus. So Furgellaria is a red algae species that will also benefit from the clearer water. But similarly to Focus, it will not like any decline in salinity or the increase in temperature. But overall, it is also predicted to be among the winners. Then we have one of the most clearly positively affected species groups, so aquatic mosses. They are predicted to do really well in the future because all of the future changes are good for them. They like higher temperature, they will like the clearer waters with more light availability, and because they are originally freshwater species, the decline in salinity is not an issue for them. And therefore the models predict a big increase. Of course, that is clearly an overestimate, but it gives the right idea of the direction and possible magnitude of change. So they are among the clear winners. And so are pond weeds. So also those will like the warmer water, the better light availability, and also because pond weeds are originally freshwater species, they will not be affected by the decline in salinity. So also they will do just fine in the future. But unfortunately, as said, there are also losers when conditions change, and many species are predicted to be affected quite negatively in the future. And first, we need to talk about the blue mussel. It's a key species in the area, and as you know, it is already living at the very limit of its tolerance for low salinity in this area. It's clearly really stressed already now from these conditions. You can see it by, for example, comparing the size of the blue mussels from Kvarken and then more southern Baltic Sea or even the Atlantic. They are much larger in the southern areas where water is more saline, which is a clear sign that it is really stressed here. And in the future, therefore, even the really small decline in salinity could be a huge stress factor for it. It could be too much, more than they can tolerate. And especially this change in salinity combined with the increase in temperature. So also temperature is a stress factor, and when the temperature is rising at the same time when salinity is declining, it could be detrimental for the blue mussels. However, the models do predict, I don't know if you can see it, but here is a small ribbon remaining just off the shore. So the models predict that in a bit deeper areas, there might still be high enough salinity and low enough temperature. And in a way, the models make sense because salinity does increase when you go deeper because saline water is heavier and also temperature declines. So there could remain some suitable conditions. But as I explained in the opening slides, the models only take into consideration the conditions in the water column and not on a sea floor. So these models, in a way, they don't know that when you go deeper, it's more likely that the soft sediment is, well, that the sediment is soft and there is no like rocks or large stones on which the species could attach. So it might be that there are no remaining suitable areas, or at least not that many for the blue mussel in the future. Another species that could be negatively affected by the decline in salinity is the Baltic clam. But this is kind of a unique species among the ones that we modeled in the sense that this might be actually negatively affected a bit by the application of the Baltic Sea Action Plan. Because in the past decades, the Baltic clam has probably benefited from moderate levels of eutrophication, because higher primary production means that more material that it can eat is like sedimenting towards the sea floor. And then in the future, if primary production declines, it could mean that there is less food for the Baltic clams, and therefore the population could be a bit less dense than what is today. But it's nothing dramatic, but the models do predict a small decline for the species. Then another important species of the soft seafloor is Monoporeia. This is kind of an easy case. It's really straightforward because it's a cold water species and the increase in temperature is predicted to be harmful for it. So it will decline, especially in the shallow areas where it is too warm. And finally, luckily, not everything is so black and white, winners and losers. There are also several species for which the models don't predict any major changes. For example, stoneworts. They are predicted to do about as well also in the future as they are doing now. So of course, the increase in light availability will be good for them, but still the models don't predict any major changes on the scale of the whole project area. Then we have chironomids. And they are really tolerant and abundant in the present day, and nothing in the future seems to threaten them. So it seems that they will do just fine, and if anything, they will maybe increase because of the increase in temperature. And finally, we wanted to include some invasive species in the study. We chose Marenzelleria. So it's really tolerant to a wide range of conditions. It has a wide niche and, well, like any good invasive species should have. And because of these conditions and these features, it is really tolerant to also changes in its living conditions. And therefore, the predicted changes in salinity and temperature and so on are not predicted to have any major impact on its occurrence in the project area. So they will be just fine also in the future and just continue their spreading. So to sum it up, we are expecting an increase in temperature and in light availability if the scenarios that we have chosen will come through. And the species that might be among the winners are Fucus, Furgellaria, aquatic mosses, and pondweeds. And then things that are expected to decline are ice, maybe salinity, and then nutrients. And among the species who are expected to decline are blue mussel, Baltic clam, and Monoporeia. And among all of these changes, things that are expected to remain more or less the same are the populations of stoneworts, chironomids, and Marenzelleria. I think I have used my time.
You have.
So
You actually have.
I will step aside and answer any questions if you have any. And I would like to thank everyone and so on. Yes.
Yes. Please check your time. I will expect you here in 20 minutes. Or rather, we will start in 20 minutes. So be here or be gone. So maybe it was a slightly early call. That will probably not work for the break after lunch. So I'll have to get another another strategy there. There's a fire in the stairway. Okay, so we have 2 talks before lunch. The first one is on a question that I am pretty sure are really interesting for many people around here. It's about sea level rise in the Gulf of Bothnia by 2100. And it's the speaker is Jani Särkkä from the Finnish meteorology. That was hard. I have not been drinking it in the Meteorological Institute. And he works with sea levels and modeling, slightly not so surprising maybe. Sometimes when you read about, when I prepare for this and read about the speakers, I check out their publications, and I think that Tytti's subject was very cool, but the coolest title ever of a paper is one by Jani. It's Effect of Nuclear Polarization on Spin Dynamics in a Double Quantum Dot. Wow, Jani, I suspect that you will not explain what a double quantum dot is today, but I guess it's hard. So Jani, do you hear me?
I hear you.
Oh, thank you. I will start to object around in 25-ish minutes from now. So please, Jani, you're up for the next 25 minutes, and then we have a couple of minutes for questions.
So thank you, and thank you for inviting me to talk in this seminar. And actually, the title Ben mentioned was in my PhD. It was quite a different topic, so then I changed a little bit field into the sea level research. So just very shortly about the sea level characteristics in the Baltic Sea. So here's a map of the Baltic Sea, which also you see included in your ECOnnect project area. And the sea level is mainly affected by atmosphere. So the wind moves the surface water, and then it gets the entire layer to move, and then also air pressure affects the sea level, and then there are so-called seas. So actually the Baltic Sea is almost like a lake, and the seas are the oscillations of the water. So kind of similar, you would compare then the water oscillates in the bathtub. So for example, in the Gulf of Bothnia, the water can then oscillate from the northern Botnian Bay up to the center Baltic Sea. And also a very major factor in the Baltic Sea is that there's a flow from the water from the North Sea to the Baltic Sea through the Danish Straits, and that's the route where also the salt comes into the Baltic Sea. And in the situations where there are long time prevailing westerly winds, they bring seawater from North Sea to the Baltic Sea and raise the mean sea level of the Baltic Sea. That's very common in the winter time. And actually there are very small tides in the Gulf of Bothnia. They are only a few centimeters, and the mean depth is 54 meters. And these most extreme sea levels, they are caused by windstorms, which then kind of push the water towards the end of base and cause these oscillations. And the highest maxima of the sea levels are the ends of bays, so in the northern Botnia Bay, in Kemi and Oulu, and in the eastern Gulf of Finland, so there where the water is able to pack and kind of pile up, and the highest maxima are found there. And actually in the map you see in the triangles the Finnish tide gauges which measure the sea level. And actually, of course, there are also tide gauges in the Swedish side, and you see actually also their locations later. And the tide gauges have 100-year time series. And so far, the highest observed maxima were at Hamina and at Kemi, about 2 meters. And next to the very important effect, which is especially strong just where the audience is in Umeå. You see here is the map of the land uplift in the Fennoscandia. And why then there's a land uplift? That's because there was this Fennoscandian glacier which has melted away, and then the earth, which was kind of a depression and pushed downwards because of the glacier, is then returning to the original level. And in the highest uplift rates over 8 millimeters per year are just in the ECOnnect project area. And actually you see here the kind of lines of land uplift, and as nowadays one can say that the global mean sea level rise is maximally 5 millimeters per year. So you see that there's a 5 millimeter line goes between Stockholm and Turku. So still at the moment in the Gulf of Bothnia, the land uplift is higher than the mean sea level rise, and the relative coastline then is at the moment kind of expanding towards the open sea. Then just to mention what are the factors that contribute to the global mean sea level rise. It's of course the atmosphere is warming, and due to that also seawater is warming, and it needs a larger volume, it expands. And the other major factor is melting of ice on the earth. The large ice sheets are in Greenland and in the Antarctic. And then there are the mountain glaciers, which are also melting, and they are causing also a major contributor to the mean sea level rise. And actually, just to remember that the meltwater from the Greenland and the Antarctic, it doesn't go just evenly around the globe, but because when the very large ice mass melts, then actually the gravity is reduced. So actually the meltwater then goes further away from the area where it melted. So actually the meltwater from Greenland goes actually more to the southern hemisphere, but in the Antarctic it's the opposite. So more of this meltwater goes to the northern hemisphere. And actually there are large uncertainties which I will talk about later, and one is this, what will happen to the West Antarctic ice sheet. And during the last century, the mean sea level rise was between 1 and 2 millimeters, at present is between 3 and 4 millimeters per year. And then something about the past observations of sea level trends. So actually this is a publication from recent year. Actually there are two ways to measure sea level. There are the tide gauges. So actually you see this here, red squares, they are the locations of the tide gauges on the coast of Gulf of Bothnia. And then it can be also be measured with the satellites from space. Actually this measurement method has been possible only from the 1990s. Actually good time series are only 20 years long. And remember that in this figure, the land uplift has been removed from the data. So what you see in this figure, that in the Gulf of Bothnia, there's a large uncertainty what is the mean sea level rise, but it could be 5 millimeters per year, but in the right-hand figure you see there's an error about 3 millimeters per year. So actually there is still not enough data to define trends well. But actually one of the most important things to see this figure, that in the northern Baltic Sea the mean sea level rise has been higher than in the southern Baltic Sea, and it is not completely understood why. One reason could be that the wind climate has a little bit changed, that there could be more northerly winds which push the water towards the Gulf of Bothnia. It could also be related to changes in the salinity, but it's a little bit open question. But really, and you also think that the tide gauges and the altimeter give quite similar results. And then just to kind of give background how myself and my colleague have made these estimates in this ECOnnect project area, what will be the sea level rise by 2100. So kind of traditionally very many people do that they just pick the number from the most recent IPCC report. But actually, these reports are a little bit conservative. They kind of a consensus opinion, and behind these reports are a very large number of different studies. Actually, our idea was then to kind of take very many sea level scenarios and combine them and kind of not only give one number, but a distribution. What are the probabilities of what the sea level could be in 2000, mean sea level could be in 2100. And you see actually in this figure there are these many different scenarios. The solid lines are the mean scenarios, and there is this 5% and 95% confidence level. They are the dashed lines. You see that for the mean sea level, some scenarios give about 30 or 50 centimeters sea level rise, but there are some over 1 meter, and when you take into account the very small probabilities, it could be almost 2 meters. So kind of using these scenarios, we can make this distribution of sea level rise. Just to mention that actually recent year there was this new IPCC report. So this actually our analysis was done 4 years ago, and actually these IPCC reports have moved towards kind of giving more weight to this. You see in the figure low likelihood, high impact scenarios, that there would be additional 1 meter sea level rise on top of these previous scenarios. That's because there's large uncertainty with what will happen for the ice sheet of Antarctica. Will it kind of a marine ice sheet disintegrate, and then the ice sheets could flow more rapidly into the sea? Because actually, if the entire Antarctic ice sheet would melt, it would add about 60 meters in the mean sea level. But actually, it's a very slow process, so it will still take quite a long time. Just to shortly mention that actually I also thought that the water from the North Sea flows into the Baltic Sea, and if there would be kind of increasing probabilities of westerly winds, it would mean that also this wind would raise the mean sea level of the Baltic Sea. But it is actually at the moment quite uncertain what would happen. And now actually here are the figure. You see in figure A is the kind of a total mean sea level distribution on the year 2100, and these figures B, C, and D, they show the 3 different components of the sea level rise and their distribution. So actually in this figure B, it is the effect of the global mean sea level rise on the Baltic Sea, and actually at the moment it is estimated as a little bit less than the full 100%, about 87% of the mean sea level rise affects the Baltic Sea. That is because this meltwater is distributed unevenly around the globe. Actually, there are then 3 Finnish cities, for examples, where the distributions are calculated, and actually the major difference between these cities is that the land uplift is different. So in the figure C, you see the estimated land uplift in 100 years, and the black one is Kemi, and you see that there's almost 1 meter land uplift, and it will be then counteract this global mean sea level rise. And also there's Rauma and Helsinki, where there's small land uplift, and figure D is this quite uncertain effect of whether the wind climate will change and increase the mean sea level. You see that actually the mean of this component D is almost 0. Also, the kind of sum of these 3 factors forms the figure A, this total mean sea level rise distribution, and you see that in the red line in Helsinki, there the mean sea level rise is expected to rise. The peak of the distribution is about 20 centimeters, but there's the last uncertainty between these scenarios. and it could be over 100 centimeters, and or in some other cases even negative. And in Kemi and Rauma, there the land uplift is higher, and due to that, then the total mean sea level rise will be negative, and at least the peak value. So the most likely scenario, there will still be land uplift will win the mean sea level rise, and the relative sea level will then decline. And now in the following slide, I will then show from this distribution the results for the cities in the ECOnnect project area. So this average value of this mean sea level rise is about minus 30 centimeters, meaning that in the most likely case, still the mean sea level will decline by 30 centimeters. And that is the low end scenario with 5% probability. And then the sea level will, relatively sea level will decrease by about 70 centimeters. And in the high end scenario, 95%, there's a possibility that there could be a small 20-30 centimeters rise. And actually these values differ only because between different cities, because there's different land uplift. In the Swedish sites, it's 10 centimeters higher land uplift, and due to that, then the mean sea level rise will be smaller. And if you just want to pick one value, to say what is the expected mean sea level rise, you can say that in the ECOnnect project area it's minus 30 centimeters. So the sea level, mean sea level will decline by minus 30 centimeters. And just very shortly to say what we can say about, I thought about the mean sea level, what will happen to sea level extremes. Actually, in the past, there's no clear increasing trends in extreme sea levels. And these, as I mentioned earlier, highest extremes are reached in northern Botnia Bay, in Kemi and Oulu. And actually in the past, in this Kvarken area, the highest sea level was in January 1984. And it was less than 150 centimeters. That's just a very special case where in the entire Gulf of Bothnia, several tide gauges had their records. And so in 100 years of tide gauge measurement, that was the highest. And it's quite unlikely that higher extreme would be reached. And in the future climate scenarios, there are no clear indications that there will be stronger winds or more frequent storms. So actually, there's also a very large uncertainty what would happen in the extreme in the future. But actually, as I showed in the last slide, even if there would be a small increasing trend in extremes, but then there is still this relative sea level, mean sea level will go down. So it would counteract that. But actually, what is the most certain thing then that the mean sea level rise will then cause the sea level extremes to globally rise at least as much. And just to wrap up the discussion, actually one thing I didn't mention earlier, but just to mention in this IPCC report last year, they also discussed the year 2300, and there is a small possibility that if there was a large melting of the Antarctic ice sheet, would be 7 meters or even 50 meters sea level rise, but that is very uncertain, but it has also been studied now. And one thing to remember about the mean sea level rise, actually it's a very slow process. The melting takes centuries. Then even if in the globe we would get the CO2 net emissions to zero, still the atmosphere is warmer and the melting will still continue. That actually, if you wanted to kind of stop the mean sea level rise, you should take out the extra carbon dioxide emissions from the atmosphere and return to the pre-industrial level. So actually one of perhaps the most certain thing about climate change that the mean sea level rise will continue, but actually just for you in this ECOnnect project area, it's just one of the safest coastlines in the world because then it has very high land uplift. It will then counteract this mean sea level rise even if the mean sea level rise would increase. And now actually if you want more details about how this calculations were made. You find in the paper of Pellikka et al. Unfortunately, it's not open access, but actually then there are 2 open access reviews if you want to know more about past and future trends of sea levels. There's a review on sea level dynamics and also sea level review of extreme events, which also includes sea level, and they are open access papers in this journal, Earth System Dynamics. So actually, this was my last slide, so thank you, and then you please ask me questions if you have any.
For doing this so clear. It's obviously a very complicated subject, but at least to me it is. But I think I understood you, so and I appreciate that. So are there any questions from the audience here? That's the problem with making stuff easy to understand, Jari. They got all of you. Vi har en fråga där. Ja, men bra. Johan.
Yeah, thank you very much for a good presentation, a very interesting subject. I just came up with a peculiar question perhaps, but when you showed that you had this higher increase in the Botnian Bay of the sea level, I started to wonder is it only land that's uplifting, or is it also the, say, seafloor of the Gulf of Bothnia that's uplifting as well?
Yes, actually, that's the entire Earth's crust actually. Just the effect is noted in the coastline actually just during past 10 or 20 years. Now it's able to measure by GPS actually also elsewhere on the coast from satellite, which is the landrise. But it's the entire Earth's crust is rising. But actually just previously the effect was actually visible only on the shoreline.
I'd say as a complement to that question, everyone with a sailboat sailing out here are very well aware that the seafloor rises. Extremely well. The sound effects of that situation is not good. So you really want a sailboat that can do some rock chopping. Anyone else? Yeah, Johnny told me that this was took a stone from his heart, as he has a summer cottage and he will be able to use it at least the rest of his life, and potentially the rest of his kids' life as well. So thank you for doing that to us. Åsa has a cabin in the middle of the sea, and you will also be able to use it. So that's good. Great. Thanks a lot, Jari. Thanks a lot for your presentation.
Thank you.
We are in plus time. We have time over. So that's very, very unusual, I would say. The next speaker will be, I thought, the only phytoplankton taxonomist I knew, but it turns out that Siv has doubled it today by teaching one of my former students phytoplankton taxonomy. So now I know 2. It's probably in a pretty esoteric and unusual way of earning your salary, but you will talk about nutrients and algal blooms in the Gulf of Bothnia. Siv is from Umeå Marine Research Center that is situated just a few, it's not miles, some tens of kilometers south of here. Varsågod, Siv.
Tack. In my world, it's perfectly normal to be a phytoplankton taxonomist. Thank you for inviting me here. And I was asked to talk about nutrients and blooms. So that's what I'm going to try to do. Now I hear myself strangely. I work at Umeå Marine Sciences Center as an environmental analyst, and I work with environmental monitoring in Sweden. So it's the national monitoring that we have here. and I mostly work pelagic, so not on the seafloors. But what I show here, it will eventually come down most of it to the seafloor as well. And I will show data from the national monitoring in Sweden, but I've also had some contact with Sirpa Lehtinen at Särkkä, so I will be able to show you some data also from the Finnish side. In Sweden, we have a national program going on since the beginning of the 90s in our waters. It's a bit longer time series if you go southwards. And we are responsible for the monitoring in the Gulf of Bothnia on this left side for you. And then also once a year, the SMHI comes up with their boat and taking a lot of samples. So that's the station net on the right-hand side here. And also some of these stations are monitored in the same or the similar program in Särkkä in Finland. So we have quite some data. We always want more. And we measure quite a lot of different variables, but the nutrients, of course, are one of the main ones. These show the inorganic nutrients for both inorganic nitrogen and phosphorus. And these are winter means. And we're talking about the Gulf of Bothnia, but I rather not say something that is for the whole system, actually, because they are so different, Bothnian Bay and Bothnian Sea, when it comes to these things. So this is the station. I think earlier Sam talked about this station as well. It was F9 in the SMHI vocabulary. We call it 813, but it's the same site. And here we have a significant decreasing trend of nitrogen, actually, in the winter. And there's no significant trend of phosphorus. These trends analysis has been done with Mankendal, and all the trend analysis that I will show you has used this type of statistics, and the data that I show you have been taken from Sveriges vattenmiljö. And there you can find all sorts of maps and plots. The situation in the Bothnian Bay does not imply really any eutrophication going on. But if we go to the Botnian Sea, it's another situation. We have no significant trends for nitrogen in the winter, but we do have that for phosphorus. And it's been going on for quite a while, and it does have some implications for the ecosystem and for the phytoplankton. And at the same time, we don't have, we have actually a decrease of inflow, or the nutrients from land is decreasing. So we kind of blame the Baltic proper for this trend. If I go a bit closer to where we are now, so we are in Umeå, but as you also said, I work at Umeå Marine Research Center. It's 40 kilometers south of Umeå. So it's situated in a place called Norrbin, and there we have some stations we've taken quite a long time now. And then also I got some data from my colleague in Finland, Särkkä, just across the Quark. And I was a bit curious, do we see the same trends? It seems that we do. These are the Särkkä data. There were no significant trends for the nitrogen in the wintertime, but we do see an increasing trend for phosphorus. And the result of that is that we will have a decreasing ratio between nitrogen and phosphorus. And this is also significant for these data. And then Örefjärden, where I work, we have the same situation. There's no significant trend for dissolved inorganic nitrogen in the winter, but we have an increasing trend for phosphorus. So what does this, I mean, so these are just nutrients. What do they really mean? And this can be a result of that. The cyanobacteria, or the filamentous cyanobacteria, so some species of cyanobacteria, they have the ability to take up nitrogen from gas. So it's not available for any other phytoplankton, but for them they have these special cells that they can take up nitrogen, which means that nitrogen will never be lacking them. They can take up as much as want. So they are always phosphorus limited. And they make large blooms, of course, in the perfect settings for them. And they like when it's phosphorus limited, because then the other phytoplanktons don't have a chance. They also like warm waters. They also like more stagnant waters, because they have these gas vesicles, so they can hover up on the upper meters. And this is what I look in the microscope. It's Nodularia spumigena. It's one of these. It's actually 3 genuses that make these blooms in our waters. It's Aphanisomenon, it's Dolichospermum, and it's Nodularia. And Nodularia is the one that is most toxic, most problematic species. Aphanisomenon, it's not also very common in our waters, but we see it more often now. But these bloom data is so hard to make good statistics on, because you have a lot of zeros, and then sometimes they pop up, and you need to be in the right place at the right time, or wrong time. Whatever you depends on how you look at it. But this one we see more often in the Baltic proper. It doesn't really like the fresh waters that we have. And it's also once 15 degrees, which is kind of picky in our waters. Aphanisomenon is much more adapted to our waters. And it's not that problematic, but we can have blooms of that as well. And as I said, it's hard to monitor blooms, actually, but SMHI has a satellite system for this. And we do see that it's increasing. This is from August 2020, but it's quite, well, in my world, it's quite cool. You can go into their webpage and see how it differs every non-cloudy day. We don't see these blooms in the Bothnian Bay. We only see them in Bothnian Sea. And also Christine knows all about this. She works at NTM-centralen for Bottniska Viken. The satellite data is not so good for the coasts, but there you need to have people calling in. And they do more and more often. And if it's because they are more aware of the blooms, or if it's actually an increase in blooms, we should be a bit careful. But as long as it's a lot of things in the newspapers and all, so people are more, well, they will call more often. But when that is said, we also see that these species are increasing in our monitoring data. This plot on your left is these filamentous cyanobacteria in Örefjärden, and it's also a significant increasing trend. So it follows what we are expecting from the nutrient data. And we see the same situation in the data from Särkkä in Finland at Molpehellona, where we have, well, it's actually a significant increase for the data, but I would like to look a little more into it. I got it last week. But we do see that it's at least an indication. We seem to have the same situation on both sides of the cork. And we also see this in the offshore data from the monitoring. So I'm making myself quite brief here, but we do see that inorganic phosphorus is increasing in the Botnian Sea at several stations. And we also see that the ratio between inorganic nitrogen and phosphorus is decreasing, which makes, we've always looked at, historically we've looked at the whole of the Gulf of Bothnia as a phosphorus limited area. But we seem to have a shift, at least some places. And this will make life more easy for the cyanobacteria that we don't want to have on the beach at the summertime. And we've just started up, 1st of March, we started up a 2-year project. We're going to look into this a bit more in detail, both temporal and spatial. Is there a difference between coasts and offshore, northern and southern parts? And also in do we see it the whole year round for these nutrient data? And also, I mean, there are some indications, some publications showing that we have the blooms earlier now, which matches our vacation plans more poorly in our view. So this is something that we will go into further. And as I said, we also have, we have less nutrients from land coming out, so we need to find out where do these nutrients come from then. We've talked about oxygen earlier today, and the monitoring data also shows that we have a significant decrease in the Botnian Sea, which we also blame the Baltic proper for, but it's something to take into account. So that was really what I wanted to say.
Thank you. I don't have to pull people screaming off the podium today.
No?
So, any questions for Siv here? Mm-hmm. Can we have a microphone over there, please?
Yes, thank you for presentation. Actually, you just mentioned in your last few words maybe an answer to my question, but you mentioned the Baltic proper, but you also see a significant trend in nutrient from the bottoms of Botnia Sea, I believe. You mentioned the oxygen deficiency and maybe a resuspension of phosphorus from old times. Do you see any reason in any higher risk of more and more nutrients diluting to the system from the bottoms in the future?
Well, this trend has been going on in our data for 20 years or so, but we still, it's ongoing, so I would expect it to be ongoing for a while further. It's quite high level still in the Baltic proper. It's not decreasing, even though our input is decreasing. So it's something that we have to look in further. Something that I didn't talk, I was actually asked about blooms in, like you didn't say cyanobacteria blooms, and right now it's another bloom that's more important, I would say, and that's the spring bloom. And the spring bloom is more important for example, the benthic animals living. And they would be, well, I would like to look into that as well. It's they need both nitrogen and phosphorus, of course, the diatoms, but also some of them like ice. So if the ice disappears, it will I guess it would, or it will affect the diatoms. We might have the dinoflagellates instead. Not so good for the benthic system as the diatoms are. So we should think about more than one bloom. So it's actually Christmas Eve just right now.
Johnny?
Yes, thanks. Thanks for very clear results. And my question is about the Baltic Sea Action Plan. We have applied it in the ECOnnect project. And what is your thoughts and knowledge of how we are reaching it? And if second is that you already said that it's increasing, although it's coming less from the land. So it is like a nuclear power station down there somewhere. Yeah, from where comes it?
Stockholm.
But what is your thoughts about the Baltic Sea Action Plan? And the decrease that we will?
We have for 100 years pumped into the system, the Baltic, quite a lot of nutrients, and they are still there at the end. But Baltic proper is, of course, another system than the Bothnian Sea. But if we get more, I think Sam also talked about it. If we get more waters from the Baltic proper into the Baltic Sea, then we will not see this decrease, even though we, on our hand, decrease the inputs of the nutrients, of course, because it's a quite large surplus there. And also, there was a article coming out now in the spring. Johan, do you remember the author? But they also looked into this Baltic Sea Action Plan and how many years do we need, and it might be a bit optimistic to think that 100 years is enough. It seems to be. But I mean, I'm in my world, I work mostly with what has been and what is now, and not so much in the future. That's for the models. But we need to have good data, and this is the data that you are using in the models. So that's my work task.
Any more questions? Oh, yeah, there's one here. But just a couple here. Oh, Johan had a question. Okay, I'll come back to you online in.
Is it working? No.
Come on, now it works.
Hello? Yes. Thank you, Siv. Well, I know you're very fond of phytoplankton, right? So, well, I think we all understood that the cyanobacteria have been increasing the past years, at least. Have other species increased also, or do you see kind of a shift in the food web because the nutritional value differs quite a lot between different species? Diatoms are really good food for the zooplankton, for example.
We do see a general increase in chlorophyll, and that's stronger than what we see in the cyanobacteria. We don't see these increases for most groups of phytoplankton. But when that is said, phytoplankton is also beautiful, but also tricky because they have these up and downs. You need a lot of data to be able to do good statistics on them. So I need more data. That's my 10 more years.
More funding. Isn't that always the bottom line?
Yeah. But we do, it's, the diatoms I've been looking into a bit. Diatoms and dinoflagellates, they have this ratio because both of them are turning up in the spring bloom in our waters naturally. And some years it's a lot of diatoms and some years it's dinoflagellates. And that fluctuates, and we don't really know the reasons why. It might be temperature, ice cover, and turbulence, probably.
Okay, I have a couple of online questions here from Juttila. Maybe not a question. I would have thought that nutrient levels from land still increase. Well, probably in some sense it is a question. Do they?
Not in the monitoring data that I am aware of. Well, the general picture, of course. There are local differences, of course.
Okay. But that's up here, or that's because the stuff you get up here from southern places, they must come from somewhere.
Yes, and that's what we are going to look into more in detail, but it's probably from the sea, actually. It's so from the runoff from the land, it's decreasing, but
in a general way,
in general, absolutely.
Then you might have answered part of this at least. Jutila follows up with what kind of trends in the phytoplankton species have you observed in the Botnian Bay?
The Botnian Bay, there's no really, there's no typical decrease or increase. It's quite stable.
Okay.
What we have seen, though, is that chlorophyll is increasing and biomass is not. So phytoplankton seem to be, there might be a shift, and I have not been able to look into it yet, but as the waters get darker, the phytoplankton will need to be more, well, they need to be more effective in how they harvest the light. And small species are more effective at this than the larger ones, so we might have a shift to smaller ones. And we kind of see that from the monitoring data because we have more chlorophyll per biomass of phytoplankton. So they get smaller and more efficient. Mm-hmm. But maybe smaller is not what we want. That's you get another ecosystem. Or maybe you want them, Johan. Since you like even smaller things than I do. So. Yes, that's true.
Yeah, it is. Any more questions? Otherwise, the morning session is done, and lunch will be served downstairs. Thank you very much. Oh yeah. Sorry. There is some serious stuff going on here.
Because you not have been belonging to the staff.
No. So, thanks, Johnny, for catching that. So, I would like you to be back about a little bit before 12:30. And I will not hunt you this time, I promise. have a relaxing lunch, and lunch is on the projects. It doesn't cost anything, so stuff your face if you feel like it. Välkomna åter från en lukullisk lunch. Med relativt lite klimatpåverkan, eller hur, Johnny? Ja, bra. Vegetariskt, ja. Och ni där hemma ser jag inte alls, men jag hoppas ni också är kvar och med. Där var min penna. Och nu ska vi fortsätta med presentationen en stund. In English! Hello! Welcome back again! Det var det där med simultantolkningen. It was with a... Yeah, okay. That was what you said, Johan. You're too subtle. Okay, sorry. We're back, and we're back online. The next speaker for this, the three subjects we have this afternoon will be started by Johan Wikner from Umeå Marine Research Center. Norbin, as before, about 40 kilometers south of here. South. And Johan is a bacteriologist, I think. Welcome.
Thank you very much,
about bacteria.
Bent, and I could understand you despite speaking some Swedish.
Thank you.
And hello all you here. Thank you for inviting me. Hello all you in cyberspace. Hope you can hear me well and see my slides. I had the privilege to join the Synoptic Arctic Survey last summer, between the end of July to the end of September. It was a 57-day expedition that we preceded with 1 week in quarantine to be able to handle the restrictions and the COVID infection at the time. And we did. Nobody got infected, and we could have our expedition. So now I just have 25 minutes, so we have to hurry to get to the North Pole quickly, right? Let's go. Just want to take you back a little bit, so you understand what a challenge this is. So early explorers, before the 1900s, we had 1,000 persons that have tried to go to the North Pole. 750 deceased. They died. No one reached the North Pole. It's a really harsh environment. Remember that. So even if you go in with a modern expedition, you know, it's some risks, of course. Will we get stuck in the ice? Will we come back before the winter hit us? I asked the organizer actually once, what happens if the engine breaks down and we, you know, get stuck there? No one really gave me an answer, actually. But let's look, why do we go there? This is a graph of the Northern Hemisphere and the extent of ice and how it has changed in percentage from 1980 to 2020, about 40 years. And it's simple in one sense, it's about 40% decline during this period, 1% per year. So of course this is a concern we have. We shall see if I manage to get this to function. It looks like that. So let's do like this and we can have a brief look at the NASA slide here. Oh no, we can't. I have to do like that. See if it's always this dilemma. It doesn't want to change slide. Sorry about that. I don't know. It's changed on my screen, but not on yours, apparently. So I think we just skip that, actually, because it doesn't follow my cursor here. So we do like that. All right. So we have this decline, and it has been done research before, of course, but the thing is that it has been very scattered in time, and it has been individual expeditions measuring some variables, but of course not all of them that we would like to have. So this is an image over 25 years for chlorophyll A, and particularly carbon. And you see that it's scattered in time. Let's see if I can get my pointer here, there. We will go in this area. This is the Lomonosov Ridge. So we came from Svalbard here, traveled up to the North Pole somewhere here, and followed the ridge here. Actually, we aimed somewhere to go somewhere here, north of Greenland in the end, to then go back towards Svalbard. But of course, for other variables, from viruses to fish, there's very little samples. And indeed, we also wanted to use the modern technique of DNA sequencing to also understand what organisms are up there in the Arctic Ocean. So Synoptic Arctic Survey is an international cooperation, a large project including about 10 countries around the Arctic Ocean, and all were supposed to contribute with at least one expedition, where we also harmonized methodology so we could compare our measurements. Very important. And then we get a synoptic, a simultaneous image of the conditions in the Arctic Ocean. So one long-term intention is to create a baseline, reference values, to be able to, in the future, compare and see how climate change will change the conditions in the Arctic Ocean. So we hope to be able to redo these type of expeditions at least every 10 years. So there's a lot of questions addressed. It's about 7 work packages involved. It's 4 different areas of research encompassing physical drivers. It's ecosystem response. It's about carbon cycling and ocean acidification, totally of 9 major research questions. But if I simplify them a little bit, one important question was, is there fish stocks up there to exploit commercially? One important question that we should be able to answer quite quickly, and I will give you some preliminary results. Another is, do the Arctic Ocean release or absorb CO2? How does it contribute to the global carbon cycle? And acidification is, of course, attached to this. Other things are to understand ecological effects of reduced ice cover. If the ice retracts, we get more insulation, we might get different hydrography in the area, and so forth. This we cannot answer on this expedition. This is in the long term, of course. We have to repeat this type of measurements and hope to be able to answer that better in the future. Same is true for biodiversity effects of reduced ice cover, of course. Will new or organisms from southern latitudes then immigrate to the Arctic Ocean and change the ecosystem considerably? So these are the type of question we wanted to answer. So let's go. We take off from Helsingborg in southern Sweden. It's like 26th of July last summer. Beautiful day. No feeling that we would go to the Arctic Ocean. At this point, we had shorts and T-shirts on. Fantastic ship, this Oden. It's operating here. That's one connection to what we're talking about in the Gulf of Bothnia, right? This winter, it has been up here breaking ice, but it's also a polar research vessel. That's really fantastic. 180 meters long. It has 4 engines of 4,500 kilowatts or 24,000 horsepower, if you have a better feel for that. It makes 3 knots in almost 2 meter thick ice. That's quite impressive. It has can go for 27,000 nautical miles, or double that, 54,000 kilometers, with full bunker of oil, and have 100 days capacity. We plan to use a little bit more than half of that. So we had some security space, right, if something would go wrong in the end. So we passed Gothenburg and get out of Skagerrak and along the Norwegian coast that usually is terrible in terms of waves. But it looks like this. Wonderful. Because it's not too fun to go with an icebreaker in open water. It's quite okay in ice, but it's not the best trip in open water. So we had some waves, of course, but 5 days later, disappeared from the ocean, just rising up. Svalbard, of course, was there. So a fantastic sight. We were lucky to have a pretty good and bright day, so we had some sight. And we were also lucky to see things like this. This didn't happen on the way down, I say. So there was some gathering of whales actually in the area. And we saw dolphins and or killer whales and so forth. So it's like an animal park for a while. So fantastic. But that was not the reason we went there. We went there to go up to the Arctic Ocean. And of course, here you see the overall track. It's about 2,000, almost 3,000 kilometers in the ice only. So about 9,000 with the transit up and down. So quite some distance to travel. So the real expedition track from Svalbard and upwards you see here. Blue are ice stations where we took ice cores and made measurements. The red ones are water station where we sampled water down to 4,000 meters depth occasionally. It's really deep. So the Arctic Ocean is an ocean, of course, and it's deep, and it's in contrary to the Antarctic, which is a continent, right? So it's very different environments in that sense. So then you have an idea where we're going. Just when we passed Svalbard the first day after, we were already in the ice. That was actually 2 latitudes earlier than Oden experienced 2016. So in that sense, it felt like it was more ice. Well, I would expect less ice in some sense. But as we've seen, it's actually the curve goes down. So we prepared our laboratories, of course, all the equipment we would use. It was good to have this long transit area. Usually they start in Tromsø and it's just a few days up to Svalbard. But we had time to prepare now because people from the Polar Secretariat had not been able to prepare instruments due to the restrictions. And well, we started to become ready. And when I was out on deck one day, a colleague shouted, "Here it comes." And there it was. Something we really wanted to have seen, a polar bear. And yeah, you may look at the polar bear, but also have a look at the ice. We were traveling in that substance. That was not easy for Oden. And actually, at that point, we went very slow. Indeed, Oden got stuck. People thought it was really fascinating. They took their cameras, went back on the deck. You know, they wanted to have a close-up on the ice bear or polar bear. What they didn't know was that actually the first officer, you know, couldn't drive through the ridge that we were stuck in. If he started to go backwards, the ice would have piled up behind, and the iceberg could have walked in. People down there didn't know that, but the first officer was quite concerned. Fortunately, the captain was on the helicopter deck above me, and he gave an order to the first officer, full force forward, despite the ridge, meaning that the propellers made a force of the ice backwards, scaring the polar bear, so it went on the side. The ship could back off and go through the ridge eventually. A little bit too close, but a really fascinating animal. One of the world's largest predators, of course. It's about 3 meters long and can weigh like half a ton, 500 kilos. So impressive, and it looks quite healthy. It's in good shape here, right? And perhaps hungry. So that it walked after us is really amazing, right? Usually animals are afraid of humans, but it tracked us. Perhaps feeling the smell of the cook making some good stew at the time, or feeling the smell of us. But you could have other type of animals. This should be ice gull, spent, yes. Is the other one a Skegness gull? That I don't know. You don't know. That's what I could find out anyway. So some other interesting animals, of course, we could experience. But with time, after the 85th latitude, animals kind of disappeared. There was very few. We could see one single seal here and there, but birds almost disappeared completely.
What latitude was that?
Yeah, 85. Above that seemed to be too harsh up there. Okay, but we were doing science. Here is the rosette sampler with it could be 24 12-liter bottles. Now I think it's like 22 because there's some instruments there. These are what we sent down to 4,000 meters. Took 4 hours to make a 4,000 meter sampling. Okay, about 1 hour per 1,000 meter, but it was just to wait. And so the days were full of sampling. We could sample in the front of the ship and in the aft. 2 different systems, but still it took time. Okay, let's briefly look at what our project we're working with. I'm a microbiologist or bacteriologist, as Bent said. These small dots here, they're rods, they're spheres, there's some vibroid, doodle-shaped things. These are the small prokaryotes, bacteria and archaea, the oldest organisms on the planet, but they're still out there, and they're still up in the Arctic Ocean. We wondered when we started, we have seen on some earlier articles, of course, it's cold up there. You see the black line here, it's temperature. And you have the scale here. So you see we have 0 degrees here. So what looks like a peak is actually just 0.5 degrees. Okay? So already at 200 meters, we go below 0. And at 100 meters, we're actually below 1.5, 1.8. We're close to the freezing point even of seawater. So a little bit surprised still that as in many other aquatic environments, the highest abundances of prokaryotes, bacteria and archaea were found in the surface water, and then declined quite sharply. They're about 1 order, 10 times lower than in more productive waters. So there are few, indicating low productivity, of course. Not too surprising. But it seems like then the light, perhaps, is our hypothesis, is more important than temperature in terms to regulate the production or the growth of the prokaryotes. But we have much to do to analyze this further, of course. Most of the data are analyzed but not evaluated, and there's some still to analyze. But there are many other creatures then. This is on the base of the food web, of course. This is a multinet with different mesh sizes on the net, so you can sample different type of plankton and nekton even. So just some examples here. You have a jellyfish here, an atolla, and you have several of these coppepods. Calanus glacialis is found here. And I think actually Calanus is something you can find also here in the Gulf of Bothnia, actually. That's yet another connection. So some similarities between the Gulf of Bothnia and the Arctic Ocean, also on this small level. But still, I'm fascinated. These small jelly organisms can still grow and have a life in below 0 temperatures. It's quite fascinating. So here's some other examples. What was caught with, I think these were caught with a beam net. We will look more at that in a short while. Crustaceans here. You have another jellyfish, Nemiopsis. I think this was the one they thought we had here in the Gulf of Bothnia 1 year, but it was Martensia instead, so it wasn't this one they were concerned about. Maybe this is one of the more fascinating organisms they caught, a sea angel. It's a naked seashell, and really have wings, so it goes like this in the water. It looks like an angel. And you have a jellyfish kind of famous. This is common in Norwegian fjords, I know, Periphylla. Ulf Bomstedt worked on that, Christine? Yes, you remember? Example. Okay, but this with fish was one important question, right? So we had these acoustic sounders that measure backscatter. In that way, you can see if there are organisms there. I think these are signals of zooplankton and nekton, which are swimming organisms in the water, and might also indicate fish. And there's also some arrows here showing where they actually sample different species of fish. Gadus is actually the Atlantic cod, and this is the ice cod. So that they found Atlantic cod here was quite surprising. This is not from our expedition, but the previous one, the Mosaic expedition, where the polar stern icebreaker was frozen into the ice for 7.5 months. 2019 to 2020, you have the time here on the x-axis, right? So they traveled with the ice, and this is the measurements during the whole travel. So this indicated there were fish there. So therefore, one of the questions, was there stocks even further north, because they went a little bit more south than we did, of fish stocks that could be commercially exploited. Swedish Agricultural University had created a beam net specially for this occasion, so you could do vertical trawls. And they worked hard for almost 24 hours. They had 24-hour ice stations, we call them, when they got time to do these vertical holes and try to catch fish. They also put out fish traps in holes they made in ice. They also put out fish lines 300 to 400 meters long with bait on them to try to catch fish. So 3 different methods to catch fish. So how many fish did they get on the trip? 5. 5, and I think almost all were polar cod. So they caught one in an aquarium for a while to give it some ice so it felt like home, and then you see how it looks like. They don't become bigger than that. They're like 25 centimeters long, so it's not too much to catch and eat, right? 5. Allo Paulin, that was the expedition leader, have already been to Brussels and reported this because the commission was really eager to know because there are negotiations going on at the time for deciding what country should be allowed to exploit these fish stocks that are non-existing. We hope that won't happen, actually. Okay, we continued. This is an image of what the weather looked like 75 to 80% of the time. Cloudiness, fog. The helicopter pilot wasn't too happy all the time. He could fly like 200-300 meters and land because we couldn't let him go further for safety reasons, right? Clear days, he could go and do reconnaissance tours for the ship. So he tried to find leads where we could go to go more rapidly forward. So that was one important strategy for Odin, to find a good way forward during the time. But they went out and they put their fish traps and holes and so forth. So yeah, when the weather was good enough, the site was good enough, some work packages and researchers could go out on the ice. But the first ones on the ice was, of course, polar bear guards, okay? Don't forget about the polar bear. They're always out there and they're difficult to see. And it's not always this clear. But out there, as you see on this slide, you have the polar bear guard there with his binoculars and a gun, sharply loaded, of course. We took these ice cores, and in these ice cores we measured temperature, we measured nutrients, we took samples for DNA sequencing, of course, to see what organisms are in there. Yeah, a bright day could look like this. We can get off the ship, which was nice, and we could have a good view of Odin like this. I think we had about -9 degrees there. It was in August. That was among the coldest we had. Otherwise, it was around 2-3 minus below 0, but seldom above. In the front of Odin, they flushed water to keep away the ice when doing the samplings, and it was created some of these foam balls you see here with some green in it. And it turned out when we looked in the microscope we had with us that it was chlorophyll because it was red when we illuminated with a specific wavelength. And if we increased the magnification, we could see it was Melocera arctica, a diatom, that also is actually present in the Gulf of Bothnia. One more connection. Okay, when traveling in ice, it's important to have a good strategy where you can go. So they used satellite images to check the ice density. Do you see the 10th of August, when it's lighter, not purple, it's a little bit less density of ice. You have the high density here. Moderate is red, and when it's green, it's low. So it looked like we could go this way down towards Greenland. But just 10 days later, things have changed, and the ice had become more dense and more difficult to travel in. So it just shows how the ice is changing and moving all the time. During one sampling, 8-10 hours, we could move 10 kilometers. Just by we were laying still, but the ice was moving like 10 kilometers during the time. Okay, so in general, we had 2 meters thick ice, but still Odin can make 3 knots in that, right? And it looks like this. I don't hear some sound there, but it doesn't matter too much. Well, there it comes. So now you have traveled a little bit with Odin in the Arctic Ocean, right? That's how it feels. And how they measure the ice thickness is with this advanced technology, a pin with some measurements on, okay? So when the flakes turn up, then the first officer can see, it's about this thickness, so I can continue, or whatever. Yeah, it wasn't more advanced than that. I was a little bit surprised. All right, so the 16th of August, we reached the North Pole, and it's not a pole like that with signs. That's something Odin brought with it, of course, because it's moving all the time. Some people didn't bring their long pants and warm clothes. They brought their instruments and played music. And it was even a graduate student from Finland actually working in Stockholm that had dance lessons on the way up. So they made a Lindy Hop dance on the North Pole. You can see that on YouTube, I think, somewhere. The fantastic mess staff, of course, treated us with some beer and warm chocolate and sandwiches and hot dogs. Great time. This is what the North Pole looks like, if you want to know. Quite, sameness in some way, monotony in some sense. It's a lot of ice and ridges and so forth. A little bit, quite good weather when you see the sun a little bit like that. And it's late, so the sun is up all the time, very light, hard to sleep. You may see nice things though, like ice bows or triple suns, different things in the ice like that. And after 5 weeks in the open sea, it was nice to see a coast again, which was the Greenland, northern coast this time. Not many people have seen that. The helicopter went out, put down their fish traps, but you can notice something, it's quite little ice. And this is actually the point in the Arctic Ocean when scientists say this is the last place where ice will disappear. It was already this little. A little bit surprising. Now, people have already made an article and analyzed this. It's, of course, due to climate change to some extent, but also meteorological conditions. Lars have to correct me if I'm wrong, but it has been winds from Greenland, pushing ice away and making warmer water coming up and created this situation. So it's comparably little ice there at the time. All right, in this area, we also took a sediment course like this, and the scientists working with that were really happy when they succeeded to take a full core 40 centimeters deep, meaning that it covered 100,000 years back. That means they can take samples now and see things happening before the previous ice age, even when Neanderthal man walked on Earth. Quite fascinating, but we have to wait for the results, what they see. Okay, the final day was coming. We had come closer to the ice age again, closer south, meaning more organisms, but also meaning a risk of polar bears again. So we were quite concerned it would be a cloudy day that would create problems, but it became a bright day. So quickly out with the polar bear guards first, of course, and then the guys here are making holes for the fish traps, and here are a group making the ice course. We worked hard. The day, it takes like 6 hours to take all this course. So about 4 o'clock in the afternoon, we were done and breathed out. Great, no fog, no polar bear. Would be great to see a polar bear again. So what happens? 1 hour later, it came. Very many good humans up there. How can I cheat them to come down? Maybe I sit down for a while and check them out and see if they can play with me for a while. Smells good. One of the crew members had a drone, so he could go and film it. And actually this bear then walked to the hull of the Odin, and they have these holes, I said, where they grease the hull. So it put in the head and checked out what was in the hull. Okay? So it likes holes in some way. And it also went to check our fishing traps, right? And it's also holes there, so it's interested in holes. Why is it interested in these holes? Well, it's not for the fish traps, of course. It's because these guys, a ringed seal, may pop up. That's their main food, actually. They eat other things too, but as you see, it's not a photograph. We didn't see any ringed seal. I suppose a careful ringed seal is a living ringed seal, so it's not easy to see them. But really fascinating to have this predator close again. That was the second time. So this is actually my final slide, Bent. I just want to make the point then, comprehensive biological Arctic expedition. I think maybe the most comprehensive, hard to estimate, but we measured from viruses to fish, as I said, but also physical parameters and a lot of chemical measurements. We made all 7 ice stations, 24-hour stations, also 8 stations with the ice cores, 20 stations in addition with water samples to 4,000 meters, and just our work package collected 1,627 samples. And then we have 17 work packages. I don't really know what the others collected. We have just summed that up, so we will see these numbers soon. But it's a lot of work to evaluate this, but hopefully not too far away. We will come with articles to present what we learned about the Arctic Ocean. If you want to know more, look at the Swedish Polar Research Secretariat homepage, Synoptic Arctic Survey 2021. Thanks a lot for listening.
I have a kind of a complicated question online that I think that you should maybe write the answer to. You could answer in the chat, I think.
Okay. Okay, is that complicated?
Well, maybe it could turn out to be. I think so. Any questions from the audience here? You said, well, but then I have one. You said you had about 100 million prokaryotes per liter, and that's low.
That's 10 times lower and more productive environments.
So we have 1 billion here. Wow, it's a lot of.
That's kind of this area just to get a feeling for how many they are, but they are very small, fortunately.
They would be, wouldn't they? Wouldn't they? Wow, I have to calculate how small they have to be. That's good. Okay. Well, thank you very much. Thank you very much.
Thank you.
We have a gift to you.
Oh yes, Johan is not paid.
Giftless.
He's not a paid member. No.
Ah, wow. Okay. Wonderful.
Too bad for you, Emma.
Is it even some fermented herring?
Yes,
it is. I love that. Great. That would be perfect. It's some to be too old.
So is it a gift or? You don't really know. So is this the computer we should use?
Yeah.
Okay, so I'll just don't mess with it. I saw your face there. Don't touch it. We all know what guys my age do to computers. So I would like to. There you are. Hi, Essi. To welcome Essi Lakso up here. She's also from Metsähallitus. Third time. And she's an aquatic ecologist which works on ecosystem services. And with that said, I'd say that we're turning the last two talks will be more on the applied side of ecology, where the first ones has been more like describing processes and potentials. You will be more, as far as I understand it, more applied.
Yep.
Yeah. Seems like I understood the schedule. That's good. Okay, I'll just get out of here. Det var inte din bild, nej.
No.
I know. It's kind of the wrong picture.
I was thinking like.
Yeah. It's cute though.
Did I
It's cute
change my
though,
slides?
but it's not the right picture.
And the next one maybe. Yeah. That one. Yeah. Thank you. So yes, hello. I will be presenting the ecosystem services results for the ECOnnect project. So ecosystem services are the natural conditions and processes through which ecosystems and the species that live within them enable and sustain human life, to be short. And in literature, ecosystem services are often divided to provisioning services, regulating and maintenance services, and the culture services. And regarding the Baltic Sea, the provisioning services are often the benefits we get directly from the nature, for example, fish and aquaculture products. And then regulating and maintenance services are the wider natural processes that benefit us in the sea. And the culture services are the culture and social outputs that we get directly from the sea. For example, swimming, fishing, and culture heritage. And in ECOnnect, we have used two methods to study the ecosystem services in the central Gulf of Bothnia. We have used MESAT, or the Marine Ecosystem Services Assessment Tool, which was developed by Inacio et al. In 2018, and then an Ecosystem Services Index, which was built by us in the project. And the benefits of these two methods were that MESAT was done for a smaller pilot areas, which enabled us to assess a high variety of different services for
different marine environments, and then the index was constructed to cover the whole large ECOnnect project area, so we got to know more on the wider changes in the ecosystem services. So first, quickly on the background information. The assessment of future changes in the ecosystem services were based on the same boundary conditions as the future climate and species distribution models. So the models that Tytti showed us earlier in the morning session. So that regarded the worst case climate scenario, RCP 8.5, and the nutrient reduction targets by the Baltic Sea Action Plan. And also it's important to note here that the models that Tytti presented us were also used in MESAT, so the Marine Ecosystem Services Assessment tool when it was applicable, and also the index was constructed based on the future climate and species distribution models. So the method was used to address changes in ecosystem service provision between the present and the future times. And then the method assessment was done for 3 separate pilot areas. We had one large area of the coast of Vaasa, that like turquoise color, Uutgrunnan Molpehelena, which was also mentioned in the earlier presentation, and then 2 smaller bay areas on the Swedish coast. So in the method, we used a set of different ecosystem services, and the change in the ecosystem services provision was assessed through a set of indicators. And what this means is better seen in this table. So the services are often rather broad in terms. So we need kind of like the indicators as proxies so that we can measure the services. For example, if you look at the wild animals and their output service, that can't be like directly assessed, and we needed to use a combination of different indicators regarding changes in fish stocks to assess that service. And for the different indicators, the present and future values were assessed separately, and then the total change was calculated with a special function of the method tool to be converted to a Likert scale category of change, which you see there, so that we could compare the magnitude of change between different indicators. And to assess the changes in different indicators, we used models, databases, literature, and expert opinions in the background. And then the category of change for each ecosystem service was then further calculated by averaging the category of change value of all the indicators that worked behind to assess that service. So for the result, this doesn't look correct for some reason. That's a shame. It has changed somehow. Okay, well, I try to explain. So I'm not gonna be able to present the results for all of the pilot areas, but I'm gonna talk about the Uutgrunnan Molpehelena pilot area. And yeah, don't look at that. That doesn't tell you anything. I don't know why it looks like this. That's a shame. But anyways, I'll try to explain some of the changes there. So the provisioning services in general are expected to increase in the future, and this reflects the EU strategy for blue growth, which means that it is probable that marine resources are used more in the future. And within the wild animals and their output, which is like up there, I already explained that it's mainly in the project area, it consists mainly of the fish stocks. So there, even though there was no change on the service level, but when we look at the indicators that forms the service, we expect that the catches of warm water adapted fish species will increase while the catches of cold water adapted fish species will decrease in the future. And within the regulating and maintenance services, the combined effects of climate change and nutrient reductions according to Baltic Sea Action Plan can be seen. So basically the negative changes are mostly connected to climate change and the positive changes are connected to Baltic Sea Action Plan. So climate change is expected to negatively affect services such as pest and disease control. So we expect basically better living conditions for alien species due to changing climate in the future, and also slightly more harmful algal blooms in the future due to the warming waters, even though the Baltic Sea Action Plan was applied. But due to the warming waters and stratification, there was still more cyanobacterial blooms expected according to the models. And negative effects due to climate change are also shown in flood protection service, which is expected to decrease. And this happens on the coasts during winters, as decreasing ice cover will enable stronger wave action during winter storms. And I'm not going to go through all of those, as there are like plus 40 indicators affecting on the background, but just to raise a few more things. For example, the implementation of the Baltic Sea Action Plan has positive effect on aspects such as the chemical conditions of salt waters, as there will be less nutrients and good oxygen conditions in the future. Also, the decomposition and fixing processes will be positively affected, as with less nutrients and nutrient cycling, with less nutrients, the nutrient cycling will resemble the natural conditions of the area better. And also, we expect better denitrification efficiency in the future. And then the negative effects of climate change are also reflected in the culture services. So basically, climate change is expected to harm negatively the culture heritage sites, both on water and on land, and that is there are many factors affecting in behind, but for example, pH, higher temperature, and also extreme weather conditions will affect that. Also, aesthetic values will decrease in the future if the human utilization of the sea areas will increase. And this is connected to, for example, wind farms on offshore areas and aquaculture. And then a bit on the discussion side. So due to the nutrient reduction themes of the Baltic Sea Action Plan, the future of many of the services does not look so negative as one might think. Also, the nutrient mitigation can generally improve the state and resilience of the sea area, which makes the sea more resistant to future changes by climate change. Also, the largest increase in provisioning services is related to the expected increase in the utilization of sea areas and their resources in the future. And that's the EU strategy for blue growth that basically is in the behind. So it's not merely that the sea would be offering us more, but we will expect that we are also requiring more from the sea in the future decades. And then, even though I didn't present now the two other pilot areas, there were like the main differences between the pilot areas were connected to differences in the human utilization of the areas, so the current and presumed future use of the areas for aquaculture industry, fishing, tourism, renewable energy resources, and restoration and protection. And the reason for this is that the pilot areas are located in rather close to each other, so most of the hydrological and chemical forces that affect on the background are the same, producing rather similar responses in each of the pilot areas. And then on the other method that we use, the index, it was constructed by us in the project. So an ecosystem services index is a measure of quantity that relates to but does not directly measure the value of nature to humans, and it can act as a yardstick of gains and losses to environment-related well-being, and it can be used to compare ecosystem services in space and time. And there are many ways to construct an index. But in the ECOnnect project, we constructed an index based on the services that different habitats and species provide in the central Gulf of Bothnia. So first on the service rating. So we use different ecologically important species that also have the ability to form habitats and or provide important services that benefit humans in the project area as a basis of the index construction. And we evaluated the number of different ecosystem services that these species produce and can thus benefit the humans. And for the connection of species and services, we used the extensive service evaluation done in Project Meriavain as a background for our own evaluation. And focus species and the common reed were found to provide the highest number of different ecosystem services in the project area of the species evaluated. And then the species were ranked for index calculation according to the number of ecosystem services that they produced. And that was done based on these categories there. And the ranking was carried out to give more value to the species and species groups that produce more services and are thus more valuable to humans. And additionally, when there are many species in a certain ecosystem and all produce a high number of different ecosystem services, it is then also more probable that they provide same or similar services as well, which gives resilience for the system and are thus valuable for the humans. And further, we did not detect any of the species from the ones that produced a small number of services to be solely responsible for producing a certain service and thus being extremely valuable in an ecological sense. So there was no need to give a special emphasis on those species that produced low level of services and had thus the lower category. So the species distribution models for reference period and the future were used in the index. The occurrence sites of each of the species were given a species-specific category value, so according to the category I showed in the previous slide. And then the models were resampled to a 2 × 2 kilometers grid cell and then summed according to the species ranking. And this is maybe better understood by this picture. So what this means is that, for example, if this 2 × 2 kilometer grid cell had the modeled occurrences of the species shown there on the left, it got a total index value of 10 according to the species ranking. And if in the future the blue mussel and focus would disappear from the grid cell according to the species distribution modeling, then the index would drop to a value of 4, not 0. So with this method, losing a species that provided many services and thus would be very beneficial to humans will have a bigger effect on the index compared to losing a species that provided only few services. And then on the results, so the total index within the project area was then calculated by summing up all the grid cell values. And there was a slight increase in the whole project area by 3%, but more importantly, there were spatial differences in how the index will change. And this change of 3% is so minor that practically it does not have any significant effect on the expected overall services on the scale of the whole large project area. But the spatial differences are what are more important in this figure. So, what happens spatially in Kvarken and Finnish coast is that in the shallow coastal areas, the ecosystem services are positively affected, while the ecosystem services in the deeper parts of the coast are negatively affected in the future, according to the index. And where this is connected to is that in the deep, the decline happens mainly in blue mussels, Baltic clams, and an amphibod species, Monoborea affinis. And they all provide a relatively good number of services, and blue mussels will be negatively affected by the combined stress of slight salinity decline and increase in temperature, while the Baltic clam will suffer from declining salinity and also the nutrient levels, and Monoborea affinis will suffer from increasing temperature. And additionally, the largest uniform area with a negative impact on ecosystem services just north of Kvarken is due to the decline also in Monoborea affinis, which has an important ecological role in deep soft bottoms as it consumes organic matter and also in the process bioturbates and oxygenizes the sediment. And in the shallow, the increase in the index was connected to the fact that many shallow water species will benefit from future warmer waters, longer growing season, decreasing ice cover, and increasing water transparency, which comes from the Baltic Sea Action Plan. And the species behind that change are the pondweeds, aquatic mosses, and stoneworts. And also the fugu species will benefit from the decrease in ice cover. And the reason why we don't see this change off the Swedish coast is mostly related to the topography of the Swedish coast. So the coastline of Sweden is steep, and it leaves relatively narrow area for the photosynthesizing organisms to inhabit. And still, like, the probable thing is that the factors affecting the future species distribution and also the ecosystem services are largely the same on both coasts, but because of the depth drop so fast in Swedish side of the coast, the resolution on which the index was calculated might be too coarse to detect similar clear change as it does on the Finnish coast. So, the negative effects of climate change and the positive effects of eutrophication mitigation by the Baltic Sea Action Plan are both reflected in the index. And when the environmental conditions in the sea changed, the suitability of bottom areas to the species changes as well. And that can be seen in the mosaic-like manner that the index and thus also the services will change. And possible future changes in deeper water species and services, and this raises the questions of possible future protection measures regarding these species or areas in the deeper waters that are expected to be affected by the climate change. And more in general terms, the index offers valuable information on the possible changes in the ecosystem services provided by a group of very important species occurring in the central Gulf of Bothnia. Thank you. This was all that I have to present.
Thank you for
a
clear talk. So let's see how we're doing here. Any questions to Essi from the audience? No. Oh, Johan. No. Oh, you
yes.
can.
Thank you very much. Very interesting and valuable to have this type of index, I think. One thing I wondered when you calculated the index was if you didn't put any weight to the value of different services. Is that by purpose, or do you have some comment on that?
Yeah, it was done on purpose. the weighing process is often a bit difficult, because if you don't know the real value that different services have to humans, then then the index would work even worse when you're not sure how to weigh properly. So that's often also in literature. It's a hard question. In a way, I agree with you that some services have more value and more of an importance to humans, but still it's a very difficult process how to weigh them correctly. Yeah.
It'll probably also differ among people.
Also,
yes, very much so.
And societies, yeah.
I'm pretty sure that I would prefer sea eagles to fish.
Yeah.
You know, so and other people would probably prefer fish. So that would be do it even more weird to give it any value.
Yeah,
but it's a good question. It's
very
a good question.
It's a
very good question.
We did consider that, but then we decided to leave it out.
Could you potentially say that, okay, if now people across the Baltic want more fermented herring, what would that be? Or food would be one of the big. Could you weight it and then calculate that this will be wrong or this will be good?
Probably.
Burn more fossil fuel and get out of the Baltic Action Plan.
Yeah.
You could.
Probably. I don't know.
You don't know.
I think that would change all of our results if that happened.
It would probably change a lot. It would be kind of interesting to put it online and let people do their own evaluation to, you know. Yeah, Johnny? Johnny.
Yes. I was thinking, what was your most learning lesson from this exercise that you have been most involved in from our project? What is your take-home message from all the exercise? Not maybe the results, but what you did and how you did it.
Oh, that's a hard question. I don't know. I learned a lot about modeling due to this very good example and showing, and I think that would be one of the biggest improvement and what I've learned. The modeling part.
Any of your results that shattered your life or your view on life?
Maybe it was surprising that we are not expecting to see that big of a change in the species distribution models. That was kind of
that was really, to me at least, that was what?
Because we were in the beginning we were expecting that. Oh, it's going to be like a horror story. But then when it wasn't, it's also a bit hard to what to say when even with the worst case climate scenario, we don't see a horror story. So how to present that.
Is it possible to, oh, sorry. I mean, this one is not I don't think anyone is being sleepless for this is kind of, we might survive this.
Yeah.
Is that a correct interpretation of that?
Yeah,
picture?
But again, I have to say it's the same as in Tytti's presentation that the Baltic Sea Action Plan does a lot. So if we don't manage to fill that in the future or probably also rather soon, then the results would be, of course, different as well.
Johnny had, I think, a complimentary question.
Maybe a comment, or actually you did answered my question very well there about the Baltic Sea Action Plan, but also that we have learned that it's not only negative effects of the climate change in our area. We see positive effects, but then it's really up to the audience to decide if the fish or in the sea eagle is important. What is your
put it online and let people.
And that is the problem also with this weighting of things.
Yeah, exactly.
Thank you very much.
Thank
you very much. And you are a member of the group, so you don't go there.
No. I don't get anything.
Well,
shame.
Well, you shouldn't be. You shouldn't be okay. You're selling yourself cheap, Essi. So the next, that would be the last, wouldn't it? The last speakers, as proper speakers, is there are two, the dynamic duo here from Umeå. It's Carlos Paz vonFriesen, which is a geographic information systems expert. Is that correct? Not. Maybe we'll see. And is a man with a lot of different expertises. He can cut trees, and he can do marine biology and geographic information system. No wonder you have a position. And then we have Johnny Berglund also here from, which kind of just keeps sitting down, which is a coordinator from marine protection and a marine biologist, which also should get up here. I guess it's up to you. You don't want him here?
No.
Okay.
Not yet.
Okay. So sit down. So the stage is yours.
Thank you. Hi everyone. My name is Carlos. I work at the county here, and I want to try to talk to you about connectivity and marine protection. Okay, one slide try to disappear. No, this is the one. I will talk about different kind of things. So I will start with a little of the theory behind connectivity. Just remember what we have to think about. And after, I'm going to start with the large spatiotemporal connectivity, and then try to see the big picture. For after, go to the connectivity in our project area, and see how it's protected. For the last, try to have some discussion and conclusion about the analysis that I have done. I suppose that many of you know about this kind of theories, and these are the biggest three theories that build the knowledge about connectivity. And I try to simplify as much I can. So maybe someone say, no, it's not so. But this is a very simple way to see this kind of theory. So island biogeography is saying big and near is good. So everything that is very big or have a lot of things very close to each other is good. With metapopulation theory, say big enough, give some quality to this, but connected enough. And the last one, landscape ecology, is giving us even more information about what's happened between this big enough and connected. Is good connection, is bad connection. And give a little more, try to put together these two theories. So when we look at the seascape, I will use the word instead for landscape. We have a lot of habitat patch. This is where we found this kind of species. And depending on how well connected they are, we can have this connected area that calls in component in this way. But we have even some kind of habitat patches that work like stepping stone. There very much happen between them. So this is helping to connect components, for example. And the whole thing is our habitat network that the species use to move in some way, can we say. But always we have this isolate part of the network. So an isolate path that is there, maybe can get some connection some years. Because like you see here, you see a static picture, but the picture is not so. It is a more moving picture in some way, that this connection not always is this. Because it's the Dutchess is exemplification about that. So maybe some years you don't have a connection, but other years you have. And that is the thing when you do this kind of analysis, try to think about that. But in some way you're always you want to get a picture, but the picture is moving, so it's very hard. We, in our analysis, we can look at the connectivity in mainly two ways: the structural connectivity and the functional connectivity. The structural connectivity is more about how everything is located in the seascape. So you see, where is the condition for connectivity? So you don't get connectivity in a proper way, but you get the condition for connectivity, and then you see, can be better or worse. And when you look at the functional connectivity, you try to see how the spreading is for the species, or the movement for the species. So you have some information, some facts, so that you know that it's moving or spreading in some way. We are not sure how everything is spreading for our species. So we just go to do analysis about structural connectivity and was showing that part. So no functional connectivity. So it's good to have in mind. We only look how the habitat is in the seascape and how close together they are or not. We have some limitation when we have modeling data, especially when we have data from the future. So the future is something that you don't see actually, so you believe in something. So for that, I limited my analysis to some kind of scale. So we have a large scale and medium scale, but we don't deep in the very local scale, because I don't believe that we can do that with this kind of data, with this input. The other thing is we try to use only a kind of minimum patch or habitat size. That is because there are more likely to be there. If we have a very small things, this is not, you cannot be so sure that the things are there. And after, when we work with the structural connectivity, I think it's better to focus on comparisons. We can't say if something is good or bad, but we can say, here is better than there, and here's the best, and here's the worst. So just remember that. We cannot say with our information that we have right now where we have good connectivity, but we can say where is better and worse. To start, I did this kind of large spatiotemporal connectivity. This is an analysis that I did with Circuitscape, and is taking as an input the depth for the whole Gulf of Bothnia, and try to simulate where is the condition for a species that want to be in the shallow part of the Gulf of Bothnia, and try to move from the south to the north. So see where they have easier to move or not. So here, the interpretation can I say is where the species can move or spread easier, or where the condition for connectivity are better. So from that we can see the Finnish part looks better, like the Quark area. But when we go to the West Botnian Sea, it don't look so good like the other part. And you see some kind of, you need to do more work to see what's happened there in the West Botnian Bay. And now, Johnny, you're going to take a couple of minutes from my presentation and show a little about current.
Yes, within this connectivity activity within the project, we have also looked into, or we have produced, we have financed and got the help from SMHI to produce these current models. And they are of course important when we talk about connectivity and how animals are spread. At least the animals that are passively spread by spores or larvae that they live in the water column. But many of the species we have studied is not spread by larvae, but by, for example, blue mussel and like spores from fucus still are, but the one that is, if we compare with the ocean out in the big ocean, there many species are spread by larvae, but that is not the case similar in the Gulf of Bothnia. It's less, but still currents are important. And I don't know, this animation we will put, some already showed this animation. We will put it on the homepage and can be visualized. We also can send them out if people are interested in them. What we did compare, of course, is to the left, the reference period, the current situation, which is this is a mean of all the models, and the left is the current situation, and the right is the future. And this is from in the summertime, June, July, and August, where we expect that most of the biological activity and species are spread, the ones that we have been studying. And as you see, there is not a big difference in this picture shows, you see meter per second current, and the speeds and looks quite similar. So some all said that about 10% more current seems to be, and they are producing a paper on SMHI on this. So there is a general small increase, about maybe 10%. We can also see what is interesting for like our local authorities, like the County Administrative Board of Västerbotten and Västernorrland. That is that we have in some area very strong currents that for example is important not only for biological reasons but also when we had an accident with oil spills in Husum. Everything went southwards because the currents was very strong and drove it southward. But for the biology, of course, we can see some major, or we can see some changes that could affect the system very much. Here are three pictures. Here the currents. So here the currents in June, July, and August. To the left here is the current, and there is the future scenario, and the picture on the right are the difference between the pictures. And we see that the red, if we go to this picture, we see that where there is red, will be an increase in current speed, and where there's blue, there is a less current speed. And here's an interesting area that it seems to be less currents, and these can have implications for the blue mussels in the area. The currents are turning out to the sea, according to the models, which might be a sink if the blue mussel larvae are spread in June and they just go out in the deep sea. They will not have a habitat that they can attach to. So we haven't used the currents within the models. It is something that we could do, and we want to try to later on to look at that also. But we have them we have to have them in our ideas and our minds. So that was the short part of currents in the connectivity.
Yes. So I will continue. And with a proper connectivity analysis, we can use this graph theory. And there we do that calls for network analysis. And a network is just a habitat patch that are connected to each other. In our network analysis, we chose to use all the patches that are over 2 hectares because there should be more resilience when it's a bigger patch. And the probability that you have the species in that part is higher too, because it's more probably that you have the right bottom. And after we use in this analysis Euclidean distance, this node distance in the sea. So this is give it our kind of a good picture how it looks like, but not accurate one. I use two indexes for see the connectivity in the project area, the landscape coincidence probability and the integral index of connectivity. These two is given us two different kind of information that help us to see how this look like. And for the whole area, we can see that the connectivity, for example, for stormboards is not the best in the whole area, and it's not going to be better. But we have for Focus and Furselaria, looks like it's going to be better, and it's not so strange because they're gonna grow more and more places, so the connectivity is gonna be better. For blow mussel, it's gonna be worse, and we know that because it's declined, so it's given the same result that you are expecting. For pondweeds, I have some problems with analysis because pondweeds will be everywhere. So without saying something, I will say that the connectivity will be better, but I were not able to get data from them because it was too much time process, and the computer was not able to do it. And after I tried to give more information, and I come from this new analysis. And it's a network that you put in together all the patches with the nearest patch. So in that way, you can get some information how the seascape is and how easy it should be for the species to spread or move. And I call this for degree of spreading. And it's very easy. It's the percentage inside a patch from the length that is the closest distance between two patches. So if we want a species to move from all the area, so I have a lot of movement inside the patches. So the thing is, should be easier to move or spread inside the habitat and outside. So give out how easy it is for a species to move to all existing patches in a seascape. And we get then a lot of numbers, so it's not so easy to see. But here we see where is the best and where is the worst. So we have some species that have hard to move in the seascape. That means it's more fragmentation. These have hard to reach some of the patches. And other are green. This means it's very easy for this species to move or spread in that part. And what we see here seems like in the future is going to be better. And for some species, going to be worse. From blow mussel, for example. And we know this is going to decline in this area. And we see even that they happen the same in the Swedish and the Finnish part. So, but now we can go to the protection. And we see very clear that the IKI target, we can reach it for the whole project area for a lot of our species. But we have some problem with the EU Green Deal. But the picture is kind of different if we start to see for each species in the different part of the ocean. Then the representativity is not as well protected. So this is a kind of a worry point for the protection. To see how well protected is the connectivity, we can use the partition of this integral index of connectivity and get a kind of connectivity value for each patch, habitat patch, in three different ways. intra, flux, and connect. Intra is very connected to the patch size, how big this is. Flux is based on how much is coming through a patch, depending on how much have in one size and the other. And connect is a more kind of the stepping stone quality of the patch. And I take two examples here. For example, patch F and D, they have a very low or not value for flow, flux, and connect, but they have a value for intra. And here F have a bigger value for intra than D. In the same way, we can see that E and H can have a similar flux, but E should have a better connect and a better intra value because its position, this position is better in this network. And here, not try to see too much. I want to show it's a very kind of complicated picture, but it's saying that it's going to be better in some places, it's going to be worse in other. For pond weights, we don't have data because I was not able to get it. And here we see that for stonewards that we was supposed to expect is going to be better or the same that was right now. And this is the protection of the 25% best patches. That means that they have the highest values for connectivity. In the same way, we can see that focus, for example, the protection is going to be worse in the future in Finland. And this not means that you have less focus. It's just that protection is not in the right place. So the focus is going to move this where they are to another place a little bit, and then the protection is going to decline. Sorry. And here I try to do the same for this degree of spreading. And then we got a lot of numbers here. But here you get what is easier or harder to spread inside the MPAs in the now and in the future. That means that it's easier or harder to spread inside the MPAs. So when it's red, it's harder. So that means that you are not protected the best part regarding to just this index. And we see here that in the future shows to be a little better maybe. So the protection will be better placed in the future. But we see that we have to work in some places. But to try to show everything, but thinking to get a kind of end picture. And this is the end picture. So you see, so looks like. It's a complicated picture. You have different things to think about and try to understand everything. And it's not the easiest one. And it's one of the things that I want to say. When you do this kind of connectivity analysis, you need to do different analysis to try to see different things in different scales to get a more bigger picture. And then you can see different parts and how it's going to be in different places too. But to see a little more, what is the conclusion then? Yeah, I can say the connectivity is not so well. That means that the natural fragmentation, we have a very natural fragmented species, and the protection is not taking too much of the best places of the connectivity. That means that maybe we need to work more with the connectivity. But in some way, we're getting a little better, but it is because they are growing more. We expect to have more in the future, but from some of them, we need to work a little more because we are not protected maybe the best for the connectivity. But if I can come with some recommendation from the analysis, point width, we don't need to think too much about connectivity. So maybe the focus will be in representativity. But if we dig a little deeper, we see maybe we need to look at the West Botnian Bay, because there we have some problems. So the protection needs to be better maybe. For stoneworks, it's almost the same, but focus on connectivity. So we have a kind of bad connectivity. So probably this needs help to protect the connectivity. Blow mussel. Here we need to focus on connectivity, but even because they are going down, try to protect or try to have a special attention in this component or a group of habitats that are connected. So we need to find them and try to protect them in some way, or see how well they are helping the connectivity. And of course, there will be special attention in the Botnian Sea. For Fursularia, there is again focus on connectivity and special attention in the West Botnian Sea. And for Focus, we need to almost the same connectivity and this component, connect a group of habitats. So we need to try to work with them and try to protect that. But for end the presentation, I want to say a couple of things that is almost for the whole area or more general things. We need to work harder with the AIKI target and EU Green Deal and try to see what's happening in these different sea zones. So try to give a better understanding and protect in different places. So not the protection is only in one part. And like I say a couple of times now, the project area is naturally fragmented. And because of that, focus have to be in connectivity. Because sometimes it's a big discussion if we want to have a big areas or connected areas. So I think when you see that it's naturally fragmented, maybe you should protect different parts to ensure that the connectivity is protected. And to the last one, the Western Botnian Sea is a part that we need to have a special attention. And some focus in connectivity, the Botnian Bay and East Botnian Sea. And the last one, maybe all of you already know that, but I think the Kvarken area is the best seascape in our project area and seems to be more naturally resilient. And because of that can be a source for the surrounding seascape. It's kind of, we have a good resilience there. So there's giving us individuals that can spread along the seascape. So there's a kind of thing that we need to have in mind. Yes, thank you for attention.
Thank you. So, any questions in the room? Not a lot of questions. Oh, now they're clapping here. There's some delay. Yes, please.
Yes, thank you. I was just wondering what kind of protection is needed for these species. What is it more important? Well, it can't be the fishing that needs to stop, or is it that there shouldn't be any housing development, or what do you mean by protection?
Protection means that we don't want to have a kind of influence in that habitat. It's depending on the species, and it's depending on what is the threat that can be there. So and depending on surrounding. If you want to protect the area with a lot of cottage, maybe you have to think about how much boats you have there. Do you want to have so many boats there, going day after day? Maybe you want then that they come together and have a part little outside to get the boats outside. So it's a complicated answer. So it's depending on the species. But the thing is, protected area, you see what is the threat right there, and see if you can minimize that.
I could add om jag hörs.
Do you don't?
Ja, jag hörs inte.
Nu
hörs jag. Okay. I could add to that that many of these we have been looking into is the shallow species like living on 2-3 meters depth. So we should be careful with like dredging and buildings, of course, as he mentioned. So and of course the what is specialty with the high coast is that it's very steep, so the areas in between the bays are of course very important, because they are like isolated according to Carlos' analysis.
I think Lars had a question. Can we have a microphone for Lars?
Yeah, thank you. I had a question to Johnny. So how you mentioned that the species are not spreading with the currents, many of them. How are they connected then? That's my question.
Many of the species that we have studied, except blue mussel, is spreading like 1 or 2 meters. Their spores are so heavy, so they are like vegetatively. They can, of course, we didn't discuss that like by birds, or that is, if they are spreading like attached to the foot of a feather of a bird, then the Carlos models and analysis are not the best. So it is natural spreading is just a few meters, so that's why many of them are, except blue mussels, are not so much affected by currents, but of course.
Okay, thank you. Thank you to you too. Now we have a break. We have a coffee break. Those of you at home can, watch the app. Those of you in here can watch the exhibition, or you can go out and eat a lot of cake. It will be your last chance for today, and maybe not, but the last chance to do it for free. And then we have the panel discussion. So panel discussionists, or whatever you call one of those, could potentially be in here about a couple of minutes before 20 past. The rest of you, 20 past. Antar jag. innan de kommer och kastar ut oss. Nu ska vi ha en diskussion här som ska ta upp lite av de ämnen som vi har pratat om under dagen. In English, once again, I freaking forgot. Sorry. I have to have a sign with speaking English. So to recapitulate, we will have a panel discussion now where we will address some of the facts and some of the talks that have come up today with people working in the area from different perspectives. We have Johan Wikner here from UMF. He is already well known by you. Lars Arneborg from SMHI. He's not only a very good climate modeler, he's also Danish, which is a very good thing. You might guess from my name that I might be kind of Danish also. Åsa Granberg from Länsstyrelsen here. What the hell is that in English? Reservatsförvaltare. Manager of conservation areas. Och Viveka Sjödin from Västernorrland, which is a climate change adapter. Wow. Wow. That was not a shitty title. What do you do? I'm a climate change adapter. And then finally, VincentWestberg from Vasa, which is an environmental director, responsible for a crap load of things. He's a marine biologist, and he is a photographer. I guess underwater photographer. Was that true?
I used to be.
You used to be? Yeah. Well, yeah. Me too. I actually think I still am, but it's currently it's in theory. So we have a number of questions that I'd like you to answer from your point of view, and I will read the questions, and you will do the answering, more or less. We could have input from the audience if that is considered reasonable. You can add a question if you like to. You out there, I do not see you right now, but I will soon. So the first question is, the northern areas and shallow seas are expected to become warmer than the global average. Can you elaborate a bit on the reasons and mechanisms behind that difference? And I'd say that Lars would be the perfect start.
Yep, I can try at least.
Mm-hmm.
Do you hear me?
Yes.
Good. Okay. So you said the northern areas become warmer.
Yes.
There's something called polar amplification.
Mm-hmm.
If you've ever seen maps of the climate change and temperature change in the atmosphere, it's always a lot of red over the polar area. And there's some different physical reasons for that. One of them is that something called ice albedo effect. So when the ice is decreasing in the summer, so instead of the sun just reflecting back from the ice surface, it's actually heating the water. So the heat stays there in the area, and it actually heats the water as well.
More than it would if it were otherwise.
It went up again, yeah.
Sure.
So that's one reason at least, and then there may be some changes to the transport of heat as well, and to the polar areas. And but I think that the ice albedo effect could be the main effect, I would guess. Then you also asked about shallow seas, didn't you?
I don't know. Yeah, shallow seas. Shallow seas.
So that's when you, it's easier to heat a shallow sea than a deep one. There's less water to heat. So if you have a pot of water and you want to cook it, boil it, it's easier to boil 2 centimeters than 10 centimeters of water. So it's quicker to.
Nothing more complicated than that.
It's not more than that. So you have to.
Sometimes
you have the heating from above.
Yeah, sometimes science is not that extremely.
But then, of course, when you look at the climate time scale, it's maybe more complicated because then you have the water can exchange horizontally and so on. So
you also lose heat.
Lose heat and so on as well. Yeah. So it's maybe not that simple, but I guess the basic effect is it's quicker to change the temperature for shallow than a deep sea.
How about you, Johan? Do you have anything to add?
Well, I have a question to Lars, perhaps. If this albedo effect is also valid for the quark area in the Gulf of Bothnia, since we're not in polar really here, we're in subarctic area, but is it still valid? We still have snow during winter, and of course, and some ice.
Yeah, so I think in many of the projections for the Baltic Sea, you see that the Gulf of Bothnia is actually heating more than the rest. And I think the explanation there is that the ice is reducing there, so there's less ice up there in the future. So more heating there than in the rest of the Baltic Sea due to that effect.
Mm-hmm. So Vincent, one for you. The link between land and sea is very important in the Baltic. What changes on land due to climate change could affect the sea the most in the future? So what connections would be even more connected?
Well, that's a $1,000 question, of course.
It is, yeah.
Difficult to
that's why you got it.
Yeah, okay. Well, I could divide it maybe into two sub-questions. The changes that are due to human land use and maybe the natural causes also. But if we look at the land use at first, it's difficult to predict what's going to happen in 100 years or 80 years. But if we think that the Baltic Sea Action Plan is not fully implemented, or if it is fully implemented, I still believe that there might be some changes in the land use due to human activity that we haven't really accounted for in the action plan or in the models maybe. Because if you look a little bit in the history, in Finland, for example, in 1950s and 60s, we drained all our wetlands and made a major impact to the sea, which are still suffering from in the sea. But we have to remember it was really important and it was necessary at the time being. So looking further in the future, we might need some new methods of agriculture, and we have a longer period of growth, so new crops maybe come, and also maybe changes in the drainage system and drainage depth. So all these kind of land use activities will also, of course, affect the sea in a way or so. So these are the land-based important things I believe that the human stands for. Then, of course, if you look at the natural causes, as we have learned today, they might be more different patterns in the flow from the rivers. Temporal differences, maybe wintertime open areas, open rivers. Maybe all the rivers will be without ice in the future, and then we'll transport a lot of nutrients to the sea. And this is normally in the southern parts of Baltic Sea. I'm not a scientist, but I believe that when the biological processes are mostly driven by light and nutrients, and we do not have the light up here in the wintertime, but when the light comes, and there's a lot of new nutrients that haven't been there before, so this might change the system completely. So these may be the big things, in my opinion.
Forestry patterns, what do you think about them? Will they be
well,
important?
yes, most probably. And it depends also on what kind of measures we take to fight the climate change, what kind of forestation methods we take, and what kind of land use, how we use as carbon sinks and so on.
Yeah.
So a lot of these measures can counteract the measures we want to when we try to preserve the sea. So we might see a battle between different kind of measures to fight the climate change, but it doesn't have to have a good effect on the eutrophication and the sea. I might sound a little bit skeptic and negative here, but that's why I think it's really important the scenarios we've seen today that we actually have in the project. They have made the calculations with the Baltic Sea Action Plan fully implemented. So we get a good positive view of what we actually can do, and it's manageable to do.
I think that's one of the things that I caught on today, that you have with it and without it, and you have climate change and you have Baltic Action Plan, that there are several scenarios that need to be taken into account, which is kind of probably obvious when you think about it, but I think was shown very, very clearly today. So let me see, Åsa and Viveka, you've just been sitting there.
Taking it all in.
What can we do?
You will probably have one of those. You'll have to work some for it. What local adaptation measures could be taken to protect the sea from climate change in the future? And I guess this kind of is an obvious question. Is climate adaptation something we need to focus on?
Of course.
Maybe Viveka should start that.
Well, as you said, it's how we use our land, and that will affect the sea most. And that is why the knowledge that this project has taken to the spotlight is so valuable. Because up until now, the focus has been, in my area, adaptation is what happens with, what type of effects will be on land, and how many risks and what consequences will this have on our society. And now we also know what will happen at the sea. And knowing that, then we can take action and adapt and make plans to increase, for example, green areas so that we don't increase the bad nutrients to the ocean, and also protect the built areas from effects of increased precipitation and intense precipitation, I think.
Yeah, with runoff, direct runoff.
Yeah.
That's probably a really important factor. Åsa, do you have something to add?
Yes, now I'm talking. Before I was a colleague with Viveka working with climate adaptation in the whole society, and now I'm working in the nature department. So now I'm focusing on climate adaptation within protected areas and nature conservation. But so this knowledge and this that has come out from this project is really important to include when we're working with, both when we're planning where we should put the protected areas, just like Carlos presented with the connectivity, and also what we should do, how we should manage the protected areas that we have. Because since what's come from this project, the most thing we can do is to maybe stop or reduce nutrification and pollution, but also with that, what can we do within the protected areas and with protected species or threatened species to help them survive and thrive, even though the climate change. And so it's definitely important both for the whole society but also within the protected areas and for the biodiversity to work with adaptation.
What will in Fika tomorrow? Coffee Fika. What will you say? You know what I heard yesterday? We need to
work hard not to reach RCP 8.5. That's the most important.
Okay. I was thinking slightly more local.
Okay.
Åsa, do you have a slightly more? I do agree with you.
Okay.
I do agree. Åsa, do you have a slightly more local take on that?
Maybe I would go for to make this. Now I don't remember this nutrient plan for the
Baltic Action Plan.
The Baltic Action Plan come true. That I think maybe it's the most important measure to, and exactly how me as a private person would do that. Maybe.
No, you don't need to be a private person now. In your work.
In my work,
in your
yeah.
On Fika, in Fika
in my
at
Fika
work.
At work, yeah.
Not at home. Fika at work.
Yeah. Work with reducing the runoff from both the forestry sector and also the agriculture sector.
Thank you. Thank you.
May I add something there, or a question?
Here? Absolutely, absolutely, Lars.
So we saw some examples today that it may also be nutrients from the south that come up and become a problem here. How do we get the rest of the countries around the Baltic Sea to live up to the Baltic Sea Action Plan? I think that could be maybe just as important.
Yeah, definitely. Yeah.
So what you're hinting at now, it's not Stockholm. It's further south.
Denmark.
Denmark.
I don't believe that. I really don't believe that. They're the most environmentally friendly. No, well. Yeah, that is, of course, a problem with the different countries and the different strategies that different economies would be probably if we should.
Yes, all have to contribute. Actually, that's
all have to contribute.
Yes.
But it's easier if you're the richer you are, the easier contributions are. That's for sure. That's kind of really sure. So Lars, there has been, I didn't know that, but there has been a change in the future, in the projections of salinity, where there will. Earlier, there was a significantly higher drop in salinity due to projections. Now, not so much. Why?
Science is moving forward. No, it's as Sam showed today, there's a lot of uncertainty around salinity. And I guess, and there's a lot of reasons for that. The global models, if you use different global models, you get very different salinities for the Baltic Sea. Salinity is kind of a balance of the fresh water that comes to the sea and what comes in from the North Sea of saline water. And when you use these different global models, you get quite different salinities. And in the earlier results, I think they used only 2 different global models. And I guess those 2 may have been on the low side there. So.
Okay.
And one was more extreme than the other. And I think maybe the biologists who like to see, I don't, I'm a little bit provocative here.
Feel free.
Who like
you're in a room of friends.
Big changes, maybe focused on the most extreme one, or more than the and maybe forgot about the big difference between those 2. Then since then, more and more projections has been added to that, and now it seems to be more spread towards 0 and maybe even on the other side of 0.
Yeah, interesting. And actually, it's pretty clear that funding policies can affect science in more ways than only one. So that's an important part of it. Yeah. So how do you choose which model to follow?
So there.
Eeny, miny, mo.
Yes. So now there has been we have had some projects where we've tried to look at a lot of different models to see, kind of find out how to pick the ones we need. So we kind of get both sides of the distribution.
Okay. Yeah.
So I hope.
So you don't use one model; you use a distribution of.
Yeah. So we use several.
Okay.
Actually, for when they do the IPCC reports, before they want the atmospheric scientists before they want to say something, they may want 20, 30 models before they say something.
Okay.
While we kind of we've managed to we have used less models, and I think there's a tradition for the regional downscaling to the oceans that people have not used as many models because it takes a lot of time to calculate.
Johan has a comment?
Yes, may I just double check with Lars then? So it's not so much a change in the pattern of precipitation projections that explain the difference in salinity measures now. It's mainly the model changes or different models used.
So the different global models give quite different patterns of precipitation, for example.
Okay, so they influence the patterns.
We are in a interface between areas where to the south there's a decrease in precipitation, to the north there's an increase, and if that pattern is shifting a little bit between different models, you get different.
So that's integrated in this difference.
So we're in the sort of in the middle between these.
Yeah.
More and less. Okay.
But as it looks now, it seems like the northern parts of the Baltic Sea tend to they get more runoff. I think for the southern parts of the Baltic Sea, it's not that sure if they get more or less runoff in the future. So I think it would, if I should guess, I would say it would be more certain than the northern part of the Baltic Sea would get smaller salinity than if you could move further south.
Okay. Thanks. Now, where do we have most bang for the bucks? Which of the effects of climate change do you think will have the largest impact on ecosystem or community structure in the sea? I'd like Vincent to start on that.
Okay,
That's a tough one.
Okay, that's a tough one. Yes, I would have said the salinity, but now I'm not so sure.
But no, that can't.
So we need. I had an easy answer. So. But maybe just the basic rise in sea temperature, and especially in the deep bottom waters in the Botnia Sea. And looking at Johnny's picture of the currents, wasn't there a circle around? I didn't understand if it was the surface currents or the bottom currents, but anyway, it's going to affect the area. And if the temperatures in the bottom rises, there might be some oxygen deficiency, and the nutrients that are stored there are all sins, they might resuspend and start something more evil that we don't want to see. So that might be one thing, of course. Then, of course, the changes in the ice cover period, of course, and of course it's linked to the sea temperature. We have a lot of species that are cold water species, and if they disappear, some of them are in the top of the food chain, so it might have some drastic effects, of course. Now I sound very pessimistic again, but you asked for the severe effects, so.
Fair enough, fair enough. No, but that's, I like the ring seals a lot. They are really, sea eagles, ring seals, they are my main concern. So the ice cover and the thickness of the ice is essential to the ring seal. So that could, and I don't know how much effect they have, but you sure see a lot of them at times. So then they're endotherms weighing about a couple 100 kilos, 300 kilos. So they will turn around some energy. That's for sure. Johan, do you have something to add?
I don't really know, because I had a similar answer. I think temperature also is the most important factor at this point.
That's kind of nice that you agree.
Well, yeah, maybe because I had managed to read a recent report, 2022, by the Baltics Group and also in Climate Helsinki Commission, and the only variable they said could really be connected to climate effects at this point is temperature. Due to partly the natural variation of many variables, but especially salinity and other things. So, and I also think about, as Vincent mentioned, the ice cover, and that will be reduced. It's related to, for example, breeding of seals, the ringed seal. It's related to scraping of the shorelines and the macroalgae establishment. So there's obvious effects you can think of in this area. And we still have ice during our coast and in the Botnian Bay, especially, and less so in the Botnian Sea, of course. So. And there are other things that you could think of, like the respiration may be also influenced and increased by temperature, and that will reduce the oxygen concentration in deep water even.
I have a question about temperature, and I don't know if maybe Lars is the best. Now we talked most about sort of average temperatures, a little bit about extremes, but I think everyone's seen the pictures that comes out sometimes when you see a lot of fish and different creatures that are dead, and it sometimes says from different parts of the world, and it can be sometimes because it's suddenly getting these extreme heat waves. What is the risks here? Is it?
That is something we need to look more into. I think that's we've not really looked that much into that, but I think that's something we need to focus on to look into how that changes.
Because I think especially in this shallow water, where there is a lot of shallow water, I guess it can rise quite quickly.
Yeah, sure. But I think, and I guess there also we need help from the biologists. What kind of indicators we should look into? So what is important for the species for what kind of temperature extremes and for how long time before the species die? I think that's an important future subject.
Yeah. So Johan, do you think you have it in you to have a short answer on this one? The likelihood of reaching the nutrient reduction targets by the Baltic Sea Action Plan. Does it need to be short? A little bit short. It's obviously a very, very important subject.
Yes. There is a very good article, 2019, that has tried to model this in the long term, 200 years ahead. And they say that, yes, we will reach the target, provided that we also reach the targets for the Baltic Sea Action Plan. Required in that sense. But then they can make a forecast, and it differs between different basins, how long time it will take before we reach non-eutrophication status. So it starts about 1 decade ahead for the Arcona Basin, and then goes slowly, not northwards really, but in different basins. But unfortunately, the Botnian Sea and the Baltic proper will take 200 years before we reach no eutrophicated status.
And that's with Lars's caveat there that if currents are coming from the south, are they included in this with a lot of
they should nutrients? Be, but they have one assumption that's important.
Okay.
They run the models at the current climate conditions.
Okay. Okay.
So climate
Okay.
change is not
Okay.
really included in this one.
Okay.
That's very important to remember when you read that.
Yeah,
Okay.
that should be kind of important.
That's the best we have right now, I guess. So, yeah.
Okay, so to my final question here, and I want all of you to answer. We could start with Lars and then go to each of you, and maybe some of you have something to add. What about this now? After today, what are how will this affect your work? Today's results or the project results mainly. What do you think, Lars? You're a modeler.
Yeah, I think it has been really fun to see how our results for the models has been used for this kind of very important results for the ecosystems. It's really and very important results for management as well. So I think that's fun to see. So I think that kind of collaboration would be important in the future for us.
Yeah. Do you have any information with you that you can use today, or is it more that you will do your models the same way in the future? Is there anything in this that will affect your models from today, or your thinking about the modeling?
Yeah, I guess it would be. That was more difficult.
That was a test if you had listened to it.
Yeah, exactly. No, but I think we need, for example, this with the heat waves and the connectivity studies is also something that I think we can contribute to. And then the salinity, of course. Yeah. We need to work on that.
Yeah, yeah, you do. Yeah. You do. Vincent, what do you say?
Well, from a water management point of view, the key message for me here is that it's really worth of implementing both the Baltic Action Plan, but also the river basin management plans around the Baltic Sea, and it has effects, and even we have seen really interesting results here, and taking these actions into account, we can actually look with a little bit positivity in the future, and not so. It's not black, it's not gray. It's quite actually light blue or something. We can live with it, and so that's my take-home message from here. A lot of different interesting results, of course, but from the communication point of view, I think it's important to address to people and basic ordinary people and scientists that it's really worth of implementing all the measures that we have in the documents.
But you're slightly happier today than you were yesterday.
Yes, with all the fika,
yeah.
Of course.
wait till you get on a scale and see what all the fika has done to you. That will quickly erase the happy smile. Åsa, what do you say?
Yes, from being sort of in the receiving side of the results from this project, I say it's really important that we consider climate adaptation when we're working with protecting and managing the nature, as I said before. And but I also think these results are really good. Yeah, it's a good pedagogical thing. It's giving us arguments, not only from the nature conservation department, but for everyone working with also agriculture and so on, to argue why it's important to reduce nutrients and work with connectivity, and so it's a sort of a piece in the puzzle with arguments on how important this is.
Thank you. Viveka.
Well, as I meet a lot of officials from our municipalities and also citizens in our community, I know that explaining the climate issue and also how we have to adapt and not only reduce our emissions, it is a question of communications. So I'm really happy that the project has packaged it all so well in the films and the animations on the website and the story map. It will help me to tell everyone about the results of this project. And it's a nice package to give them. Yes.
On that note, how long time will this be available for? Is there any dead time for it when you take it down? Forever? Forever. Forever. So it's forever.
Yeah.
Forever. Yeah.
Perfect.
That's good. But there's not like in a week. No. Good. Good. That would be a shame. Done. Johan.
Yes. Well, I also start with the models, and I think they have shown some very interesting results, and that it's very good to use them in this type of very complex questions, which is hard to handle in your head. So I think we should, rely on these results to some extent. But I also want to put a word of caution, because we know that the natural variation is great, and some of the models may not have all the functionality or parameterization in them that make them be totally true at the same time. I also note the results from these models that, for example, the ecosystem services still show quite small changes, as you also noted, Bent, in your summary, right? And they could be also both positive and negative. And a little bit comforting in some way that at least in the quark area, maybe the climate change effect from that point of view isn't that great. Also the focus didn't change that much. Maybe it was a little bit positive because the ice didn't scrape that much. We shouldn't remember or forget that at the same time, the climate change is a great problem in many other ways. In some areas, people won't be able to survive and feed themselves in the future, which may cause great migration. So although in our environment, it might be not that bad, it could be really bad in the long run anyway. So that's my message.
So, thank you very much. Do you have any comments from the audience here? Anyone feel that they've learned anything today? That was a shitty question. Of course you have. Then I thank you. I guess when Johnny stops being a teenager and put down his phone, he will come up. he will come up and manage the administration of those. Tack Johan. So thanks a lot for doing this. It was excellent. A very good kind of what do you call it? Knitting together? Knyta ihop. Knotting together. Connectivity of today's talks. So I guess that we have a couple of minutes left now. You can be seated up here if you want. You can be seated out there if you want. Whatever your feelings are. And now Emma Andersen from Metsähallitus will come and say a couple of words before I say the very last words.
Yes, thank you. Is this on?
No. Yes,
yeah?
It is. Okay.
Yes, I will now show you our homepage where you can find all the reports and links to the story map and our videos, animations, everything we have produced in the project can be found here. And the webpage is ECOnnect2120.com. And here you can find information about the project. And here is the links to the story map. We have created it in 3 different languages: Swedish, Finnish, and English. And here we will upload the reports, and we have written 3 different reports about these 3 packages of of the project, and we also written a summary report which will be uploaded here, and the physical participants can also find copies outside in 3 different languages. And if you scroll down here, you can also find our Twitter, Facebook, and YouTube. And on YouTube, we have we have all the videos, animations that we have produced. And now we will show, as we are here for the future, we will now show you a video from the future, so from year 2082 in Kvarken.
För nästan 60 år sedan var jag ung och tänd på att rädda världen. Jag tror att hela mänskligheten just då var orolig för hur illa det var med naturen och hur klimatet höll på att förändras. Här längs med Östersjöns kust var havet speciellt nära våra hjärtan. Vi insåg att havets framtid låg i våra händer. Eftersom vi förorsakat förändringen var det vi som skulle ta ansvar och agera. Men vad gjorde vi? Inte gjorde vi så värst mycket. Jag bara skämtade. Vi gjorde allt vi kunde. Jag är speciellt stolt över att vi lyckades minska våra utsläpp av växthusgaser. Det krävdes viljestyrka av oss alla. Och kommer du ihåg problemet vi hade med övergödning i havet? Tack vare ett ihärdigt arbete minskade näringsläckage från land radikalt. Annars hade effekterna av klimatförändringen i havet varit mycket större. Vi tog också hand om våra maritima arter och deras livsmiljöer genom att skapa flera skyddade havsområden. Vi valde platserna för skyddsområden noggrant så att det skapade ett nätverk för olika arter att röra sig i. Överlag lyckades vi minska på människans påverkan vid kusten, återställa förstörda områden och hantera föroreningsproblemet. Vi började också fiska på ett mer hållbart sätt och lade fisk som braxen och mört på våra tallrikar. Kan du tänka dig att denna slags fisk då kallas för skräpfisk? Braxenbiffarna som är så goda, det var ett ganska enkelt sätt att hålla balansen i havet och hjälpa de överfiskade arterna. Vi uppnådde allt detta genom att vi jobbade tillsammans över landsgränserna. Under min tid blev också samarbetet mellan länderna ännu starkare. Det krävdes vilja och engagemang av alla kring Östersjön och Bottniska viken.
Skulle vi fortfarande ha detta vackra och unika hav av bräckt vatten om vi inte hade agerat
tillsammans i tid? Jag tror inte det. Vad tror du?
Yes, so we wanted to end this on a positive note. And before I hand back to Bent, I just want to thank you all. Thank you for the presentators, for giving very interesting presentations, and the panelists for their discussions. And also, of course, the participants, both you here in Umeå. It's been really fun seeing you all after this time, and also to the online participants. Thank you.
So, some very last words. Thanks, thank you, Emma. This is a wonderful work to have to be here and actually get paid for learning a lot of stuff. I like that. I like that. Normally, I get paid to teach stuff. Today, it's the other way around, which I like a lot. So I can next time. And of course, I agree with Emma. Thanks you all for being here. Also you online. Major thanks to you that have contributed actively. It's been a lot of very interesting talks, and the words that are, if you make kind of those word maps, there will be two words that are dominating. It's scenarios and it's uncertainty. There were words that were really, really, really common today, which isn't bad per se. It just adds variance. And I really liked your last comment there. We should be kind of careful with saying that this is great, this is not great. Essentially, this has been a lot of material, but that gives a lot of information, but also gives kind of this baseline of how about next time in the Interreg 28 to 32. It is what I would like to really see, where models have been better, maybe, Lars. Salinity has been kind of optimized, and so on and so forth, and how much of this is then kept still in the system. Also, a back calculation. We know in 10, 20 years from now, some of those scenarios or possibilities, and which way did it go? Actually, we can calibrate stuff, which I think is not maybe the most important knowledge from today, but a really, really important one that you should have a ECOnnect 2, the what do you call it, uppföljare. Like vad heter det på engelska? Sequel, that was the word I was looking for, sequel. Thank you very much. So, finally, I'm 62 years old. I'll be very, very dead. 2120, that's for sure. I really hope so, anyway. And so will all of you. So to end on a positive note. No, but some people won't. Some people alive today will live in 2120. They will be alive. Not a lot, but some will. So the whole what do you call it? The whole scale of this project is in one human's lifetime, and some of them are alive today, and they will be there and say, well, they were right in the Fukus anyway, or something like that. I think that's a perspective that I at least like. It's in one human's lifetime that we are talking here. So it's not in the way distant future. It's not like 2300. Who knows? It's in my granddaughter's lifetime, so to say. So we should care. Should keep caring. So thanks a lot. Oh, finally! I was counting. I wasn't really sure. Tack så mycket. Thank you. So thanks for today.